o'clock they think they'll come at 11. So he's also like you, as a colleague. His wife is in Varangal.
Ah, yes, yes.
I told him, why don't ask the people here, because it is in NIT,
That's also very difficult.
Although that's a better campus than here, ranked.
That
Varangal is ranked. There is a renewal ranking today. I saw that. I think, I think Varangal, Trichy is 9, Anna University is 12 or 13. See, the problem with Tamil Nadu is they are politically a problem. So they don't want to become a part of, it was supposed to become center for excellence. But the politicians don't like that. Because the minute you do that, they lose control.
yes.
See, that's the problem. Especially Tamil Nadu, tremendous reservations. So that's always the problem. They don't lose the control. Yeah. play with those programs, because if you run them, it gives you similar plots, right? But what I suggest is go through the MATLAB code, see how it is coded, okay? And that way you understand, and you can vary the small things, you can adjust, and you can see what happens. Otherwise, you will never learn. You know what I mean? Now the math, there's a lot of math, but we won't have much time because there's more in depth. And as I said, since you may not have background in a lot of different aspects, it's not possible to understand, you know. So instead of me spending a lot of time in the math, I'd give you more essence what that is, so you guys can use the book and go through them, you know. That's my suggestion. Okay? So any questions? Ah. Okay. Okay, I think I can show you. I think the paper is listed yesterday. So it is there. I'll show you. Okay? So it's like at the bottom you see that there is always yeah, I'll show you. I know what you. So you did run two papers there were. One was the iteration one and the other one was the discrete time. Travis, I'll show you that. So right. There are that's in the paper. Yeah, I gave you more examples you can play. So, but the code runs and all that, right? Yeah. I just want to make sure. Yeah. So the best is to play with it, and we'll talk about it because those are reinforcement learning stuff. Okay. All right. Okay. So just for motivation, yesterday, remember I didn't show you these plots. One was traditional control schemes cause instability. Now remember we talked about it. I didn't show you. Because remember, the reason it is causes instability is primarily because the A matrix and B matrix get changed. And it has the random variables, the delays and stuff, remember? So that causes instability if you ignore it. Okay? And in general, people know that for control systems, delays causes havoc. So here it's a random delay, not even deterministic. So that's the main thing, and you can see there are two plots. One was, there is no delay and losses. If I take the original system without the network, it nicely converges. Now the same system, now I have the AZK, BZK, things will blow up. You can do the simulations very easy. Okay, number one. Number two, now optimal design, we talked about it. Right? If you're using optimal control or nonlinear control, they require the system dynamics. Right? We also talked about it. And since the delays and packet losses are random variables, and they are part of the A and B matrices, you don't know those, you only know the distribution, even that is an assumption. So as a consequence, you don't really know A and B if it's a linear system. Okay? And the other thing we also talked about is the traditional optimal control works backward in time. I explained to you, and it requires full knowledge. Where we already talked about it, right? So those are okay. All right. So we also talked about we are going to use adaptive dynamic programming because the dynamic programming requires the dynamics. It is another way of coming up with optimal control, right? Whereas the dynamic programming is the other way. One is the calculus of variations. That's the old method. Dynamic programming was developed in 1950s by Bellman. And so we are going to use dynamic programming. It's a lot easier because that helps us to look at the temporal difference error. We're going to talk about that, which is used to design controllers. Temporal difference error comes from reinforcement learning. Okay, this is how you bridge that. The reason it's called adaptive is because system dynamics are needed in traditional dynamic programming. But since we don't have it, we are going to have some sort of adaptation, and that's why it is called adaptive dynamic programming. All right? So here is a basic thing here, a flow chart. You see that how we are varying this. This is the temporal difference error, and then you're using the value function. So this is a traditional policy and value iteration, that one of the papers. This is the paper that simulated, the policy and value iteration. And the thing is, there is a drawback. Okay, so there's a drawback. Remember I told you about the Riccati equation or the JB equation. There is no closed form solution. So you use the policy numerical methods, you hold the sampling interval, and you are iterating within the sampling interval. Now you really need to have a significant computing power, because to find a solution, we don't know how many iterations you need, okay, to solve that equation, which is Riccati or okay. So as a consequence, what happens is the papers that talk about that approach, they really don't consider the real-time effects. Okay, so we used time rather than that. So you can see also, if I'm taking one of the problems, if I use 1000 iterations, it nicely converge. But if I change it to 10 iterations, things will blow up. You see? So what does it tell you? It tells you that the solution is not complete, and if you stop it halfway through, the numerical analysis methods diverge rather than converging. So this is the problem. Okay, so we don't want to use it, and we don't know if the system dynamics are unknown. I don't know how many iterations do you really need. So those are the reasons why we use the time method. Okay, so I also gave you a slide. This is the paper, 2012, the one that I gave you. Okay, and I think in the slides there's also, I listed them. Intro to oral. If you look at the intro to oral slides, you will see that name, Dirks and Jagannathan, 2009 or 2012. Yeah, that is the paper. It came out in Transactions on Neural Networks. Okay, so you can see that people were using policy iterations. So in 2012, we used what we call time-based. So basically, we don't use iterations. We update the weights once a sampling interval, and we make sure that it converges and the optimality is reached as time goes to infinity. So there's a difference. Okay, in their case, you can make it optimal along the path. In our case, it takes a while. But in practice, what we noticed was you really don't need a very long time to converge. It converges very quickly. So this is the benefit actually. Okay, so this is what we call time-based. It's a traditional adaptive control approach. Okay, so that's what we are doing. And we also talked about, you see this picture where you had delays and packet losses and all that. And we also talked about issues, right? One is the network-induced delay. Either constant or random, right? It is a problem. We also have packet losses. And we also briefly talked about network protocol effects, right? And we did TCS, and so network imperfections cause uncertain dynamics, whether it's a linear system or a nonlinear system. Okay, and I won't go through this. You can read them. Transmission delay is a big challenge. Okay, and it takes, you see that from the top to the bottom, it takes from the sensor to the controller and from the controller to the actuator. It's a round trip time, right? And packet drops are another bigger problem, because the data from the sensor doesn't reach the controller, and from the commands to the actuator may not reach the actuator. Okay, so there is a problem there. Okay, this issue is fatal, right? We talked about it's open loop. It becomes open loop. And so that's the issue there, okay? And timing is an issue. So we talked about, there are two protocols. One is the TCP/IP, which is used in the internet. The other one is called UDP. Okay, UDP doesn't have a feedback. So the question is, how do the protocols dictate how much delay you need, what information is available. We can use that information as part of the controller. Okay, so and the other thing we talked about is the quantization. I know somebody asked the quantization, and it clearly says quantization is basically you don't have infinite precision. Okay, and remember, we use A to D and D to A hardware even now. And when you are using those devices, there is a finite word length. And it takes a number, it converts into number of digits, right? There's a round off and all that problems. And that can cause problems. It's proven actually. So read this part, okay? So what happens is, you see there is a quantizer on that side, and there is also a quantizer on this side. And there are two quantizers typically. One is static, where the range doesn't change. The other one is dynamic, where the range you can change it by using a zoom parameter. And so the benefit is, the dynamic is, it basically can go as much you want, and you can show some nice properties with it. And so we're going to look at that, and there's a MATLAB code, you can play with it. Okay? And now here is the protocol effects. All this stuff we have talked about it. So here is the AZK and BZK that we talked about it yesterday. So here you can see this is a TCP. And so this is a TCP, this is a UDP. So in a TCP, you get the measurement output. This is a delay, this is the loss, packet loss, delay, and this is the feedback. So there is always a feedback from the protocol that's used to the observer. Because you don't have the states, you have to use an adaptive observer. So observer, what does the observer do, guys? It estimates the states, some of the states. That's what it's doing now, okay? So that estimated state is basically goes to the controller, and the controller basically goes through the quantization and everything. So this is TCP. TCP provides a feedback, not every instant, but so many packets. Even for the internet also, the same thing happens. It's an end-to-end protocol. So it goes all the way to the end, and then the feedback comes back. But a lot of times that feedback is delayed. It takes a long time. So if you take a course on computer networks, you know that there's a delay. It's an end-to-end protocol. Okay. So this is UDP. This UDP is usually designed or used for sensor networks. So when you have a sensor with a wireless connectivity, the sensor is sampling at a very high frequency. There's no reason for us to have a feedback, right? Even if you miss, because let's say you're measuring temperature. The change of temperature over time is not fast. So you can lose 1 or 2 packets, okay, and still reconstruct the actual signal. So in a UDP, you see that there's no feedback, and so this is the UDP information, you know, and UDP is used for sensor networks and stuff like that. There are a lot of different applications, okay. Now there is also difference between network control systems and stochastic dynamical systems. A lot of times people have that problem, right? So modeling, so when you say stochastic control, this is very clear. You got to realize that. If you have taken optimal estimation, anybody has done Kalman filters? I see many people. But I know you guys don't do the derivation. Did you look at the derivation part of the Kalman filters? Okay. So there it's basically done in stochastic. So the difference is the system is deterministic. I don't know whether you notice that. You add a process or a measurement noise. That makes the whole system stochastic. But here, the actual matrices A and B contains the random variables. This is a fundamental difference. A lot of people don't understand that. So, and you saw that in the derivation where A and B becomes a function of, you know, the actual packet losses and stuff. So if you look at Kalman filter, the way Kalman did is you took a deterministic system A and B, and then he added the process noise, and Y you have the measurement noise. Since process and measurement noise are white noise and it's a bunch of random variables, the overall state becomes random. And therefore he is looking at average values. It's a lot different with NCS. So you got to be careful understanding that. Okay, so that's the difference here. And the other one is in the NCS case, the ultimate system is time varying. Now, why is it time varying? Because of the delays and packet losses. They are varying with respect to time. Okay, and you can also include process and measurement noise even if you want it. So there is an extra term in the derivation that pops up, and I'll show you extra term. But otherwise, the optimal control policy, everything is identical to the deterministic system. Okay? So you can remove the process and measurement noise, but still the system is stochastic. Okay? So you see that addition of process will have additional terms for stochastic Riccati equation. So that's basically a little difference between that and so here is the general stochastic optimal control under TCP, under UDP. So here you are using the psi. The psi is basically the protocol set, and is a zeta. That's the protocol set under UDP. So it's a conditional probability. Now the other thing I wanted to tell you was, if you remember, we study what we call controllability and observability. This is a very important result in control theory that does not exist, which we need to be proud of. It doesn't exist in a lot of things. Now I know a lot of people don't understand what that physical meaning is. Can somebody tell me what is a controllability meaning? I know how to check it. I ask my students, immediately they write those equations. What does controllability mean? Uh-huh. Mm-hmm. See, that's why I asked that question. I'm telling you, these things you probably, that's what, remember yesterday I asked you, what is the difference between? So anybody has a better answer? I'm telling you, I have went through so many countries, people still don't understand this. There's a physical meaning actually. So anybody want to take a guess? So, well, let me say, I'm going to give you a homework. I want you to come back tomorrow and tell me the physical meaning. Guys, you need to know this. It's just not a piece of math. You have to have a piece of math, but it has to have a physical meaning to it. What is controllability and what is observability? In a very layman language, that's all I wanted to, and why do I care? Okay? So, but here what I wanted to show you was, if the original system is controllable and observable, we have proven that the network control system will also become observable and controllable. Okay? So that's the derivation that is there. I'm going to skip it. As I said, it's in the book. Okay? So that is important, because without that, we really cannot design anything, right? So that's very critical, but I want you to, before I answer that question, I want you to do a little homework for me, and you explain to me, as if I'm your student, what is controllability in a very layman's language, and what is observability. Okay? Huh? That is what it means. But what is the physical meaning? So what will happen if I don't look at it? You know what I mean? Yeah. That's what I want. And what does observability mean? So physically I need to know, let's say if you are from industry like him. Yeah, he will ask the question, why do I check it? Right? Makes sense? I'm from industry. I need to know really, why do I care? I don't like the math, so why do I care? So let me ask you, let me rephrase it. So let's say if the system is not controllable, what does it mean? It doesn't matter. Doesn't matter. If the system is not controllable, that's what it means. I'm just telling you. You're repeating it in a different language. So if the system is not, if it's not controllable, so what does it mean? Yes. That's what she said. Yeah. Okay. You can always Google and stuff, right? I think these are the in-depth understanding. It's very needed.
Okay. Okay. So any case, so what this derivation is showing is, if the system, original system is controllable and observable, you can prove that with the NCS dynamics, the network, you can also show the system is controllable and observable. So that stuff is in here. Okay, so you can, I will skip the math, but here is the math to prove that it is, you know, with some Markov parameter, Topolis matrices and all that stuff. And finally, you can show that the system that with the AZK and BZK is also controllable and observable. Okay, this is to rigorously prove that we can do something with it. Okay, I won't tell what it is, but all right, you can do something with it. Okay, so that stuff is there. You see, there's a lot of math. I won't go through this, otherwise we won't have time. All right. So this is the distributed network control systems. We're going to look at it, where you have a shared communication network, okay, and you have multiple controllers and actuators. Now, what are the applications? We talked about smart grid. Remember that, or you can talk about the CAN bus on an automotive system, controller area network, where you have different subsystems use the same common bus. All right. So that will do, I think, in chapter 8 or 9. At the end, we will deal with those. All right. Any questions here, guys, except the controllability and observability, which you can tell me? Yeah. So the UDP is used if you need some sort of an acknowledgement. So UDP provides an acknowledgement. Acknowledgement is basically what happens is you have a big packet in the internet. Yeah, handshaking, yeah. So what happens is that it's an end-to-end. So you send a your message will be divided into a bunch of packets, right? Each packet has a number, specific unique ID. And that goes, and remember, the internet routing, it can go different routes. And then what happens is when it reaches the destination, there is a scheduler, it looks at the ID and it rearranges that in a proper manner so that it reconstructs the message. This is how we do our emails and all. Okay, so what happens, because the routes can be different based on the real time, okay, in the internet routing, So whenever a packet comes, depending on the TCP parameter setting, you can get an acknowledgement to the sender, every packet it receives, or once in so many. The purpose of the acknowledgement is to retransmit or not. So TCP has the feature called retransmission. So if the acknowledgement was not received within a time window, that's another parameter. Okay, by the sender machine, it retransmits. You see, and what is the purpose of retransmission? Because let's say if that packet, one of the packets in the message get dropped. Let's say you have a long email you have written, and that is translated into, let's say, 100 packets, for example. And the sender machine will keep sending the protocol. There's a protocol running on the sender. There's one running on the receiver side. So destination. So what happens is the sending one will be sending, and it takes different routes. So assume that one of the packets get dropped. So the ID, it checks the ID and it knows the sequencing. And what it does is, depending on how you set the internet parameter setting, it can send an acknowledgement every packet it receives. And that comes back through a different route to the sender machine. So if it didn't arrive within the time frame, then the sender machine will keep sending those acknowledgements. So there is a drawback for that. That's why the UDP has come. What is the drawback? Because imagine your network is being congested. And because of the congestion, it takes longer to get acknowledgement. And if you don't properly set it, your sender will keep sending those packets. It creates more congestion. So TCP has the transmission, that retransmission property. UDP doesn't have it. Because the purpose that is because like sensor networks and all, you will be sampling at high frequency and you are transmitting large quantities of data. Why you have to have a acknowledgement? Because the problem is then your network gets even more congested very quickly. So they don't want to have it like lot of control applications. If you lose a packet, you're okay because you have enough sampling frequency so that you can manage. That's the main reason why you do that. So yeah, I have taught network courses. So and as I said, my master's is in comp sci. Yeah, so this is very critical. This is very important. You need to know, but it's not that difficult actually, the networking course. Okay, all right. So any questions here, guys? I think this is my last slide. So I just want to give you, there are a bunch of slides at the end. Read them. Gives you some basic things, some of the differences, what are the challenges, and quantization can also cause instability. So quantization, random variables, all that network induced delays, they can cause and destabilize the system. This is why we are doing it. Okay, all right. So that's number one. This is lecture one, like yesterday we covered. It took half an hour. I thought I would finish in 10 minutes. All right. Okay, so let's go into Lyapunov stability. So remember, as a control thing, it's very critical that we show some stability. Because of time, I will skip a few things and we'll go through, I encourage you to go through the book, some of the basics on stability, So you have a system, you can draw the block diagram. Here is a nonlinear system. Y is the output, okay? And you can write it in a Bronowski canonical form. x1 of k plus 1 is x2, x2 of k plus 1 is x3. So this is very typical with any of those mass damper systems. You remember F equal to ma, right? x1 dot equal to x2, x2 dot equal to F over m, right? So things like that, and you can see this is what they call Bronowski canonical form. And you have a linear system, and here is a solution in discrete time. X of k is, A is the state transition matrix, a to the power of k times x of 0. That is the response due to initial condition plus response due to the forcing function. There is a u is basically the forcing function. Okay? And there's an example, I encourage you to go through that. It's not that hard. Savings bank account, all of us have an account. How the interest gets compounded. You can use this simple things. Okay, there's a little MATLAB code, you can run it. And there's also norms. How many of you studied norms? A little bit. So there is a lot of stuff in there. The other books, if you look at my name, there are other books have a lot of details about the norms. Okay, so there's one norm and stuff. Why do we need the norm? Why? That's why I said, yeah, why? Another homework. Go back and look at it. Why do you need that? I think these are important. It's because you might know where to use or what to use, but you never really spend time, okay? So this is one norm. One norm is absolute value. Two norm is the Euclidean norm, which is basically the distance, okay? So infinite norm is the maximum. There are physical meaning behind it. So there's one is the mathematics. So that's not enough. That's what I keep saying, that just knowing the math operation. So you need to know what is the physical meaning in there. Then only you can answer that question. Why are they using infinite norm or Euclidean norm? Yeah. So yeah, unfortunately we cannot cover all this. That's why. So here I gave you the pth norm, the infinity norm. You see the maximum operator at equation 2.110. Then you have the matrices also. You can actually do what we call induced norms. And in a matrix, so you can put them as a basically a vector, and then you can do the same. And you can see there is an infinity norm, there's a pth norm, and there's also called Frobenius norm. Normally in neural networks we use the Frobenius norm. And that's square root of A transpose A. If A is a matrix, and A doesn't have to be a square matrix. Because you multiply A transpose A, like you said, there's singular values pop up because it's not a square matrix, it's a rectangular matrix. The rank of the matrix, when you multiply changes and you might have zeros. So those things will pop up there, So Frobenius norm is what we normally use for neural networks because those weights typically are not square. They are basically rectangular weights, mostly rectangular matrices. And so we use Frobenius norm, okay? So all that stuff is here. You see that Frobenius norm is trace of A transpose A. Now, why is the trace operator there? So go back here for a vector. You see that's one norm. So absolute value of each of the elements, and then I'm summing it up. What is the outcome? It's a scalar or a vector. And is it positive or a negative value? And why? I know that absolute is there. But why is that you always want to have an absolute and it's positive? That's my question again. I know it's absolute is there, so it is positive. And why do we care? All norms are always typically positive. Okay, another homework. Go back and look at it. And check and see why norms, why do we use norms, and why it always a positive. Okay, there's a reason behind it, okay? All right. So there's a quadratic forms, like I think that's what you are saying. If X is a vector, Q is positive definite, positive semi-definite, there are definitions here. Negative definite, negative semi-definite, because you use those in your Lie-Apanau, okay? And then here is a quadratic form, X transpose X, Q times X basically is greater than sigma min and less than sigma max. Sigma is a minimum singular singular value. Now what is the difference between singular values and eigenvalues? What are eigenvalues? Okay. Lambda I minus A equal to 0, you might have done that, right? I want you to check what is the difference between singular values and eigenvalues. That's another one. Okay. So singular value decomposition, essentially you can take a matrix and you can divide that by using 3 different matrices. Okay, you can see that there is 2 matrices U and V. These are singular directions basically, and then you have a matrix which is sigma, which consists of all the singular values, and you can see zeros. And that can give you the rank and so forth, right? The eigenvalues and singular values. I want you to look at these actually, okay? And normally when we design controllers, you have certain properties on the nonlinearities. One of them is Lipschitz continuous. So we talk about this, what is Lipschitz continuous? Basically it means that it's differentiable and that derivative exists. Now why do you need that? Now why do we need all this? Remember, we do this in calculus. Okay? So why do we need all this stuff? Why don't we just ignore it? Yeah, I should be able to say that. Why Lipschitz and all, why do we care? I understand that. That is right, that's what you do. But why do we check? Why do we need to check? That's my question. Okay, homework. Okay, so we need to check it, but my question is why? Why do we care? All right. So here you can see that you basically show that you take x-axis x and y, 2 points, and then you try to find the values, corresponding values, f of x, f of z, and then you find that, and that basically looking at the slope if it's a two dimensions, right? And so that's basically Lipschitz constant, but then there's a reason why we do that, because we have to make sure that certain properties are satisfied. Okay, so I want you to tell me that, when I say it's basically the meaning, these are the things you stay with you. and I think if you remember this, it's not the number of courses you take. Education is a component that stays with you even if you leave the portals of a university. Remember that. So I may not know exact derivations because I can't keep up, right? But I'm able to give you or understand when somebody is saying why this and why that. That's very important. Yeah. Okay. So uniformly continuous. So continuous is one thing, uniformly continuous, right? So the higher derivatives exist and is also smooth. And these are required. And there's a reason why we need that. The same thing in discrete time. Okay? So take a look at it. Okay? And there are a bunch of stability conditions. Asymptotic stability, Lyapunov, boundedness. All right? And boundedness means that, you can see that here is the bound and the system trajectory stays within this. Once it enters, it will never leave. But it stays there, and it takes a time, t naught is initial time, capital T. Within the capital T, the trajectory has to come within the bound. Now, why is that boundedness more powerful than asymptotic stability? Because this I can tell you, the reason why asymptotic stability is not preferred is only a theoretical result. Typically, it's very difficult to prove asymptotic stability, especially because you have noise, disturbance, there are so many things. So therefore, practical form of stability is boundedness. So you show that it's close to your, where you have to reach. And the size of the bound, you can actually control that. That's called UUB. If it's a purely Lyapunov stable, you will not be able to control the bound. So Lyapunov stability says L is positive definite, the Lyapunov function, L dot is less than or equal to 0. Okay? So unless it is less than 0, it's not asymptotically stable, right? But here boundedness essentially shows that, but that's very theoretical form of stability. Okay? So here boundedness is more important because there are so many different things you will end up in practice. UUB is more powerful than so the same thing in discrete time. Okay, I'll skip the interconnected systems. In the nonlinear stability, remember that we talked about here. If there exists a Lyapunov function, the equilibrium point is stable in the sense of Lyapunov. Asymptotic stability is the first difference is negative definite, then it's asymptotically stable. And globally asymptotically stable is that function is global, and you have the constraint L of x goes to infinity as a norm goes to infinity. So that's the global. There are some examples. So try to work it out, okay? And those are important. There are a bunch of examples, okay? So these are homeworks that is given here. You can see that L is defined as x square plus x1 square plus x2 square. That's always positive for any values of x1 and x2. Then you take the first difference, and then you basically show that it is bounded or whatever, okay? Now, there's a huge difference between continuous time and discrete time. So that's my PhD work. When I was doing it, two things I've done. I made it very easy for people to do discrete time proofs. Okay? We won't have time to discuss this, but before that, people were breaking things, and there's a reason why, and I'm going to explain that very quickly. The second problem was the neural network, machine learning stuff, because I needed that stability to prove convergence, okay? So now, what is the difference between continuous time and discrete time? So let's see, I don't know, there's no board here. I can write on it? Okay, so where is the pen? Oh yeah, that's good. Oh. Is there something I need to turn it on? Tap it? Is it? No. Yeah, pen. Select the pen. Yeah. Yeah, I think that's right. Okay, so you can see that for a screen we need so many engineers. All right. So in continuous time, remember that you select a Lyapunov function E is equal to E square, right? Let's say. And then you take the derivative V dot is 2 times E dot. So the V dot is more like a proportional to E dot. So it makes it easier when you are deriving update laws and adaptive control and stuff in continuous time. Now if you do the discrete time, okay, so let's say my discrete time function V is equal to E square of K, the same thing. So what is V dot in discrete time? Delta V. So what is delta V? Delta V is E square of K plus 1 minus of E square of K. So you can see that the first difference in a discrete time is nonlinear. In this case is quadratic. Whereas in the case of continuous time, it basically becomes a linear with respect to the first derivative. So what happens is, when you are proving stability in discrete time, you are dealing with nonlinear stuff. Everything gets squared, and it's very difficult to prove to show the proofs. So what they did before I got my PhD, in the case of adaptive control, they used to break that Lyapunov function into two parts. One for the error, one for the parameter update. In continuous time, you put together. And so when you separate it out, you have to use an assumption called certainty equivalence assumption. So I eliminated all that as part of my PhD. So and I showed how to easily do this discrete time proofs. Yeah, in early 90s. So those are the changes. That's why yesterday I was telling you, if you get a PhD, you have to have a mark on everybody should know you. So that's the basic thing, you know. So that's why in discrete time it's a lot harder to prove anything. Okay. Now, why is it important in discrete time? Because remember when we were taking the continuous system and we are adding those network effects, it ultimately becomes a discrete time system. Yeah, that's why. All right. So you study this, and you can see that the first difference becomes quadratic. You don't need the pen. Use the. I know, that's the other part. So then you show x1 of k plus 1, you know the dynamics, you plug it in and you simplify it, and you get that, and from there you show that norm of x is less than 1, and therefore you can say some stable, you know. All right. I don't know whether I can. This one? That's all you need. Okay. All right. So this is the global stability. So there are examples. Here you can, now is this system linear or nonlinear? Huh? Is that system linear or nonlinear? Why is that so hard? So that's nonlinear, right? Why is it nonlinear? There's a quadratic term, but let's say if it's not quadratic. Let's say x1 times x2. Is it linear or nonlinear? Why? You have the product. Two states, right? Okay, so you can see that there are some proofs. And, you can go through this, okay? And I also gave you the controller design, like here. There is an example, x1 of k plus 1 is x2 sine of x1, x2 equal to square root of x1, x2 plus u. You can actually pick a Lyapunov function L equal to x1 square, x2 square, the delta L, and then you plug in those dynamics, then you select your u of k equal to this, then you get first difference equal to minus x2 square of k. So that's negative semi-definite or negative definite? And why is it semi-definite? Huh? So x2, whatever values of x1 is, x2 in delta L will become 0 only when x2 becomes 0, right? So it's negative semi-definite. So basically you can only show the system is stable in the sense of Lyapunov. So here is some other things that for linear systems, this is the discrete time Lyapunov equation, A transpose PA minus P equal to minus Q. Continuous time is A transpose P plus PA equal to A transpose P plus PA equal to what in continuous time? A transpose P plus PA equal to? In continuous time. So homework, go back and look at it, okay? This is the discrete time. And there are some other things here, you can look at it. So autonomous versus non-autonomous. So it's not the same as removing the operator. So non-autonomous means there is an explicit dependence on time. That's why you see a K there. And why do you get that? Because you might have a disturbance. And the disturbances typically are varying with respect to time. Okay? So here is the time varying definitions. So you can go through all that. This is the nonlinear side of it. And there's an Lyapunov extension we call the boundedness, UUB. So L is positive definite and delta L is less than 0 for x greater than R. That's basically the set R. Then the system is uniformly ultimate bounded and the norm of the state is bounded within the neighborhood of R. Okay, I'll skip all that. Okay, stochastic. This is very critical. So you see that in stochastic, typically you have, this can be deterministic. This W is basically either process or measurement noise or a disturbance. Okay? And that's what causes the whole system to be stochastic in traditional stochastic control. And typically W is the Gaussian process random variable representation. So you see that the mean value is a x naught. Our initial state is always deterministic. These are assumptions that we make. So this is what we use for NCS, asymptotically stable in the mean square. Okay, so basically the same idea, except that you are saying the expected value of x minus xc, the equilibrium point, the norm of its square. So that is the Euclidean distance. Okay, is approaches 0 as k tends to infinity, then we call that asymptotically stable in the mean square, Lyapunov stable in the mean square, bounded in the mean square, bounded in the mean. So these are standard definitions in stochastic because of the stochasticity. You know that you take the mean, expected value becomes the mean value, right? So some people use probability. So they say that asymptotically stable with high probability. So they are all the same. The probability between 0 and 1, they show that is close to 1, you know, all right? So, okay, now remember yesterday we talked about this optimal control. So if I have a time varying system, x of k plus 1 is ak, xk plus bk. A and b are time varying, right? So I want to optimize an infinite horizon value function v star, minimum of this. That is the horizon goes from k to infinity. This is the quadratic term that's equal to x transpose pk times x. So the optimal control, you see that this is the Bellman equation. Okay. Now the Bellman equation, somebody was asking me what is temporal difference error. So you see that v of x of k is on the right hand side. I brought it to the left hand side. Okay. So I brought it to the left hand side. You remember yesterday we said v of x of k is the time to go from k to k plus 1 plus k plus 1 to infinity. It's a recursive equation. So what I did here is I brought the v of x of k from the left hand side to the right hand side, and the difference between this is called temporal difference. Why? Because the value function at x of k plus 1 and the value function at x of k, the only difference is this is k plus 1th instant, this is k. So a lot of times this is considered as a temporal difference error, or this term for optimality has to be 0. This is called the Bellman error. So in a normal circumstances, for optimality that has to be 0. But when you are using neural networks or some other approximators, it won't be 0, so you equate that to a little error, epsilon. And you use that information to tune the weights. So that is called the temporal difference error in reinforcement learning. You see? So that's basically because of the difference between k plus 1 and k. All right? So I'm going to use the word temporal difference error. You need to know that. Now, why is that temporal difference error we use? That helps us to make reinforcement learning approach for real-time systems. That is the reason. because if it's 0, that means it's optimal. Okay, remember we did that in calculus of variation, partial h over partial u equal to 0. That's exactly the same. And in real thing, you won't have a 0, you will have some value, and the goal is to drive that error to close to 0, and you will see that. I'll show you this Bellman error, you will see that going to 0. What is Bellman equation? This recursive equation is called Bellman equation. Okay, any questions here? So from there you obtain the optimal policy. You see the optimal policy? The optimal policy, you need A, you also need B. And you also need kernel matrix P, which is the solution of the Riccati equation. And the Riccati equation also requires A and B. Okay? So here is the discrete time optimal control linear systems. If I have x of k plus 1 is this, here is the finite horizon n minus 1, and this Sn is the terminal weighting matrix, Q is the weighting on x, R is the weighting on the U. So when you increase Q and R, that means you are putting more effort. That means you are saying that my x is very important. This is for regulation. Regulation means you want to go from any value to any desired value. Okay, and so when you increase the value of the matrix, that means you are saying that it's very important for us, and you are driving that smaller and smaller, the error. Okay, so R is basically weighting the control input. So when you crank up R, that means you are saying that my U is very important. I really want really smaller values of U. That means I want to really minimize my U. Okay, so this is the Riccati equation, S of k, and this is the Kalman this is the gain matrix, you can see, which requires A and B, and then here is U equal to minus kk times x. For a finite horizon, the gain matrix, Kalman gain, is a time varying. Okay, so a traditional stabilizing control, usually we use k to be a constant. For optimal control, k has to be varying. That's the difference. Remember that. So for any system, even for A and B are constants, for finite horizon, k has to vary with respect to time for optimality. So that means that it's more computationally intensive compared to stabilizing control. Okay, so this is the same thing. How do you come up with those equations I showed you yesterday? X of k plus 1 is A and B. Then here is the value function. I can rewrite this as a recursive equation. Look at that, how I rewrite it. From k to infinity equal to k plus 1 plus k plus 1 to infinity. Now, if I move this v to the right hand side, this becomes 0. That becomes the temporal difference error. Reinforcement learning. So then what you do, you use a quadratic function for v, and you take that v of x of k plus 1, v of x of k, and from that last equation, right, and v of x of k is x transpose pk x of k, v of x of k plus 1 is x of k plus 1 transpose p of x of k, p of k plus 1 times x of k plus 1. But x of k plus 1 is given by this equation. So you plug all that stuff, then you get this Hamiltonian. Okay, then you take partial of h with respect to u, then you get the same stuff. You take this and plug it back into the Hamiltonian, you get algebraic Riccati equation. It's very simple. So the same result you get whether you're using dynamic programming or the traditional optimal approach. Okay, yesterday we saw these slides, but these were inserted for a reason. And you can see that you need A and B precisely. Okay, doesn't matter whether it's a system is linear or continuous. So now stochastic linear discrete time control, basically you are taking this A x of k. Remember I said this is traditional with a process noise. Okay, so what is the difference between that and this? You follow the same. Okay, so you follow the same derivation, v equal to x pk x of k. You see an extra term here? That's what you're going to add if you have a process or a random noise. Okay? So you add that and you see that V of x of k plus 1 is this plus q of k plus 1. And why are you adding that? That's because you have the W, the process or process noise. This is the stochastic. Then you manipulate the Bellman equation and you have two terms. One is you see that the same kk. So this is same as your deterministic term. Okay, there's no change. So if you look at the Riccati equation, you have pk, which is same as the deterministic, and you have another equation because of the noise, the W. You see that? So there will be two equations when you are going from deterministic system to a stochastic system, because essentially you have the process noise. Otherwise, the optimal policy is the same whether you are using a deterministic or stochastic. Okay? So that's important. So that's the difference between a stochastic optimal control versus a deterministic optimal control. So what is the difference in terms of the system wise? The system here, you see that the system has a process noise which is a W at the end. And that W is a Gaussian process, it's a random variable. Whereas A and B are constant matrices which are deterministic. You understand that? This is what I explained to you. The difference between this stochastic optimal control versus the network control system optimal control, because there A will have the stochastic or random variables. Don't forget that. You see the difference? So even if you don't have W, A and B are still stochastic. That's the difference. Okay? All right. So the infinite horizon essentially shows that W times P infinity, it converges, P converges to a steady state value, it becomes algebraic Riccati equation. The same thing, K becomes a constant which is a steady state value. Now remember, even though that is a steady state value, that's not the same as any constant gain K. If you pick any constant gain K, it won't be same as K infinity. It's called suboptimal control. Yeah. Okay, so even though it's the same constant, but it's not the same constant, actually. So this is a finite horizon. So certainty equivalent stochastic value function. So you are using the same Bellman equation, you are getting the optimal. So you see that now I'm putting e's everywhere. That's the expected value. That's the only difference there. And then you have, there is a terminal constraint. There's an extra equation for a finite horizon, which doesn't exist in the infinite horizon case. And then you see that those are the value function. One, if the top one is the value function, the second one is the for the terminal value, and then you get the stochastic Riccati equation. You have an extra term there for the terminal constraint. Here is the optimal policy. It's very similar to what you got there. So read that paragraph there, because there's a lot of essence in there. So it talks about what is the difference between NCS and this, what is the stochastic value function increment, all that stuff. So I want you to read this, because a lot of times people don't read this. They only look at the examples, but there's a lot of meat. So remember, I was asking you all these questions. They're all in there. Okay? So we spend a lot of time trying to explain that, and people ignore it. That's what happens. Okay? So now you see that AZK, BZK. Now I brought it. You can actually add a extra term, WK, but you don't need to, because it's already there in stochastic. Okay? So now the Q learning. Remember, this is another thing we're going to use over and over again. Okay? We're going to have a break in about 2 minutes. So what I did, I took that and I wrote a Q function. The Q function is nothing but your Bellman equation. Now what I'm doing is I'm splitting this into Z and U. You see that? Z is a state vector, U is the control input. And then I have a matrix in the midin, and then I'm writing this again, the same augmented state vector. So this equation comes from this equation. And what is H? H has got all this stuff in there in the middle. So the goal is, if I want to relax the dynamics A and B, I'm converting the optimal problem into adaptive control problem. So how am I converting it? I need to estimate this H matrix. You see? So if I estimate this H matrix in real time, then I take this term, invert that term, and multiply it with this. That becomes my optimal gain. That's simple as that. Okay? So if you look at the Q function, here is not there, but remember, when you look at this regular stochastic Riccati equation, let's go back here, algebraic Riccati. So if you remember this equation requires A and B. And from there, I'm actually solving, UK equal to K infinity times X, right? That's what I'm getting. And what is K? K is R, B transpose P, B transpose P times A. So I need A and B. But I don't have A and B in the case of network control system. Both are unknown. So I have to find a way to come up with K value. So what Q learning is doing is, I'm actually converting the problem into an adaptive control problem by using this Bellman equation. We call that as a Q function. And I'm writing like augmented state like this with the H matrix. If I can estimate the H matrix by using adaptive control method in real time, the elements of the H matrix, then I take this element, this whole thing, invert that, multiply by this, that's nothing but my K. Simple as that. So by doing that estimation, I don't require A and B. This is how we are able to avoid the need for A and B. This is how we are doing it. And this approach is called Q learning. You see that? So I took the Bellman equation, I kind of mathematically I made it smarter by removing it as Z and U on the left hand side, Z and U on the right hand side like a quadratic. In the middle I have a matrix. And that matrix I'm trying to estimate it as an adaptive control problem. And once I estimate it, I look at the bottom row. Okay, and then I take this transpose inverse times this, that becomes my gain. And mathematically we saw yesterday. Go back to your oral slides. Okay, so here, that's what you're doing. And how are you estimating it? Basically, you're using the temporal difference error. So here is the estimate of J with respect to K hat with K minus 1. So this is called temporal difference error. Okay, so the temporal difference error is the error in the estimated value of the value function at K and K minus 1 or K and K plus 1. And we use that history of data to actually pose this into adaptive control problem, and you get an update. You see this? This is how I'm getting a parameter tuning of this. This is a least squares approach. Standard least squares approach, and I'm trying to get that parameter update, and once I get the H hat bar, I can reconstruct my H matrix, and once I reconstruct it, I look at the bottom row, and I take that diagonal element, invert that, multiply by the other element, that gives me my control gains at every instant of time. Then U equal to minus K times that, you don't need A and B. Okay? And you're going to play with those code that I showed you. All right? So that's what I wrote here. U1 K hat times this. You see that? I take that diagonal element in the second row, I invert that, and I multiply by the other element. That is KK, and that's same as that. So it shows by lemma 1 the optimal control estimation calculated with the adaptive estimation of Q is equal to the optimal control U1 hat equal to U2 hat. So that's a theoretical result. You've proven that. Okay? And so this is the stochastic case, and you see that the same thing you're going to do. and we can show that the same Q-learning control in stochastic domain. Okay, so I'm going to stop here, guys. We'll continue. So let's have a break. It's 11:10. Let's have a 5-minute break. Let's be back in about 5 minutes. Got it? Otherwise, you will having delayed lunch again. All right? Okay. So does it work? Okay, good. All right. So let's do this example. Okay, so this is an inverted pendulum example. You may have to do it as part of your tutorial. Okay. Now remember, I just want to tell you, when Professor Vera sends you the code, right, you are going to send them one at a time, right? In the slides, you will see this example in the main program, example 2.8 or 2_8. That's the main code. You run that one, it shows up all these plots. Okay, this is how I renamed it when I was fixing this version issue. Okay, so I don't know, I only looked at 2023, but you said it runs in 2018 also. Yeah. Runs. I think the reason is the Riccati equation discrete time, the MATLAB changed the syntax. And so when that's why, so when we run that in the old one, it has a different syntax than in the new one. That's basically what was causing that. So I redid it just to fix that part. Yeah, anything I write, it won't be a problem because we basically built. But when you are calling from some of those MATLAB code, that's where I was telling yesterday. You know, there were issues. Yeah. Yeah. But otherwise, it should run. So how are we going to do the tutorial here or down in the lab? To bring their laptops? Okay. They can run it. Yeah. I think that's very critical. I think you may want to try it out. Okay. All right. So here is inverted pendulum. An inverted pendulum, you know, that is inherently unstable system, right? So here we are trying to stabilize it at the same time doing optimality. That's why I said optimal by mean optimality means it's also stabilizable. There's no, it doesn't, you know, it basically goes without saying. When you are claiming that your controller is optimal, that means it's also stable. Okay. So basically here you see that the dynamics are in continuous time. We had a noise, white noise. You see that it's a distribution from 0 to 1. And we're using a Q-learning. It's not a network control system. We're just a simple Q-learning based system. And so I'm assuming that dynamics is unknown. Okay, the dynamics is unknown. We don't have any network because this is the background part of it. So I still, if I need to really do that, I have to solve the Riccati equation. So I'm not doing that. I'm using directly the Q-learning that I explained to you. Okay, and you can see on the right hand side that the tracking error basically with unknown dynamics, they nicely converts to become 0 because this is a regulation. So I'm starting with any initial value and I want to drive all the states to 0. You see? And even if I don't have A and B, I'm able to show that. And how I'm doing it is just like I explained to you in the Q-learning. So you can see that the augmented, somebody was asking me, the augmented state is essentially the original state, then the change in the state, and some other quantities here. That's the augmented state. And you see that W is basically the noise, and there is an initial control. We call that as a admissible control. This is very important for optimality. How many of you heard of admissible control? There's a difference between a regular control and admissible control. So I'll tell you the difference. In a regular control, it's bounded. Let's say you want to start with a bounded input. Admissible means it's needed as part of optimality. Admissible means that cost function, remember that when you plug in the control, should not be infinity. It should be less than infinity. So that means that it should provide you with a finite cost. Okay, so in the book there's a definition of what is admissibility. So you need to start your controller as an initial admissible control, not initial bounded control. Now why is that? Because let's say your cost function, okay. So these are very interesting things. I'd like to write it, but we won't have time. So look at this. So let's say you have a summation k equal to 0 to infinity 1. Is that becomes infinity or it is less than infinity, guys? Huh? So it's 1 is bounded. Let's say my control input is u, is bounded, right? So if I sum it up, what do I get? I get 1 plus 1 plus 1. So what is this? Is this less than infinity or equal to infinity? So basically that, even though the controller is bounded, doesn't result in a, so that is not acceptable. That's why we really need to have 1 to the power of k or whatever here, some constant times this, so you have 1 plus half plus 1/4, and ultimately this series will become 0. So that's what we call this. This is the initial admissible control policy. For optimal control, that's required. The initial admissible control is needed, and that's an assumption that we make, you know. So we make that assumption, and everywhere you study, we need that. Okay? So then what happens is, you see that W1, this is basically that basis functions we are generating, and once you have that, then you have your the learning rate 10 to the power of -6. You basically do the simulation, and you show that all of these states converts to 0. And you can run this as part of your stuff there, okay? So this is a discrete time in nonlinear system. Now you can see that f and g are nonlinear. You have this value function, the same as in linear systems, but you have a discount factor called gamma. Now this gamma guy helps you to converge that, gamma, as the k goes to infinity, that keeps going down. So basically what you're saying is a discount factor, because you don't know the future reward values in reinforcement learning. Therefore you want to put a discount, because since you don't know what will be the future reward, okay? And mathematically what it does is it helps us that value to stay within less than infinity. That's why you do the discount factor. So the gamma has to vary from 0 to 1. So 1 to the power of k, so that keeps decreasing, all right? So this is basically, discounting makes initial time step more important, and traditional learning usually learned during the first few time steps. So this is very important. We use that. So keep that in mind. The same process. You do the Bellman equation, recursive equation. You take it to the right hand side, and then you take partial with respect to u. You get the control policy. You take that and plug it back. You get the HJB equation. Okay? So the same approach you use both for linear systems and also for nonlinear systems. Okay? So you see that this delta V is gamma times this minus VH. This is called forward difference operator. And more important is the temporal difference error. The Hamiltonian is basically nothing but the temporal difference error. Okay? So there is also some derivation for the nonlinear system, just like I showed you in the stochastic domain. So you follow the same thing. You take the partial, and remember, this is what I was saying. There is two equations. One is the control input everywhere else, and at the final time step. This is called terminal constraint. You use the same derivation, and then you can simulate it. So here is a nonlinear system, f and g. F is given by this. So there is a MATLAB code example 2_9. Okay? So you can see f of x is nonlinear, and g of x is also nonlinear. Here is the c. There's a random disturbance. So this is in discrete time, stochastic Q learning. And you do the same process, and you can see that how the regulation errors converts to 0. Okay? So the other example, inverted pendulum, was a linear example. This one is nonlinear example. But the approach that you are following, defining the Bellman equation, and then you are basically taking the partial derivative with respect to u, that approach essentially the same. No difference. Okay, unfortunately we won't have time otherwise if I go through one of those derivations. Okay? Okay, so I still have to cover the neural network background. I only have a couple of slides. That's all I have here. So I didn't put much. Okay? So This is called a two-layer neural network. Now, how many of you, let me ask you, have taken a course on neural networks? So basically, you're missing all the prerequisites. So the prerequisites for this is you got to know a little bit about adaptive control, you need to know a little bit about optimal control, you also need to know a little bit about the neural networks. So Q-learning you're using for linear systems, remember that, right? Without, you can relax A and B at the same time. Neural networks do the same thing for a nonlinear system. If the system is nonlinear, then, so that you know, remember you guys said the Travis paper? That paper essentially relaxes the need for F. G is known there. Okay, so when you run the code, it requires G, but F is unknown. F is, you don't need F. Okay, so in my slides yesterday I showed you, I used an identifier. The identifier relaxes G also. Okay, so that comes from adaptive control. So let me ask you, how many of you have taken adaptive control course? So, you guys taken adaptive control? Where did you guys take it? Calcutta? Calcutta University. How about you? Huh? NPTS course. So what does that mean? I don't know.
Sir, there is a online, the government of India, they have created
This is Vidyasagar, non-Vidyasagar.
all IIT professors mainly.
Oh, okay.
They create a online lecture, video lectures basically, and it is freely available. It's called NPTEL.
Oh, NPTEL. Oh, okay.
Full form is the national something is there.
Okay.
So they are actually all courses by different group professors they have uploaded, and it is freely accessible. Like MIT, they have created.
Right. No, that's nice though. That's nice, yeah. So I think maybe for those who have not taken adaptive control, that's the way to learn, right? Because you got to have the background in the linear systems are very important, right? The basics, controllability, observability, all that stuff. But you also need to learn how to do the, you know, so we covered like reinforcement learning. We went through very quickly, but that's needed. You also need the background on nonlinear systems, right? Because everything is nonlinear. And then you have the linear systems, nonlinear systems, adaptive control, optimal control. So that's what I was going through. Remember all that stuff in within what? 2 lectures. It's impossible. So I think you need to have that information in order to understand this. So you see the technology where it's going now. Yeah. So you can't skip something. If you skip something, then you probably won't understand it. Yeah. Any questions here, guys, before we get into neural networks? So the neural networks basically are approximating the dynamics of F and G. Okay? Either you do that, or you can approximate the value function, and you can approximate a neural network, the control policy. So you need at least a minimum of 2. Yesterday somebody said about an actor critique. So one is called actor, which generates the control policy. The other one is called a critique, which approximates the cost function or value function. So you need 2 neural networks. And when you're using 2 neural networks, you need 2 sets of weights, for one each for the network, and you are adjusting those, so it's still an adaptive control problem. So what is the difference between adaptive control and neural network control? So I know some of you took adaptive control, right? So both you're using adaptation, but there's a difference. What is the difference? So how many of you took at least knowledgeable in neural networks? Not much. Okay, nobody has neural networks. Okay, so that's important here, because that code uses, the nonlinear code uses the neural networks. So let me give you like a 2-minute high level thing, okay? So neural network control is a nonlinear adaptive control. That's the one word thing. So traditionally the adaptive control is mainly done for linear systems. People expanded that nonlinear systems by using an assumption called linear in the unknown parameters. How many of you heard that linear in the unknown parameters? In the IIT lectures. Linear, so if you have a nonlinear function, it has to be written as linear in the unknown parameters. So what it means is, so you take a function f of x, and you say that it's written as some constant parameter values times some basis function. So this means that this f is proportional to the basis, right, with theta is the linear in the unknown parameter. Basically, you're writing that. This is a traditional adaptive control. It uses that assumption called LIP. Okay? LIP. So, then why are people interested in neural networks? So, in neural networks, we replace this by W times phi of x, where phi is the activation function. This is called linear in the unknown weights. Okay, this is a single layer neural network. If I have a two-layer neural network, then I don't need the basis functions. So I can write the W of x, f of x, equal to W1 transpose sigma times V transpose, or W2 times x. So this is a two-layer network. You have two layers of weights, W1 and W2. Then you don't need a basis functions. That's the benefit of it. But what is the drawback with the two-layer? You have to find a way to adapt W1 and W2 so that it converges. And that's the problem. Okay? So how many of you understand what a basis function is? I know some of you said you took linear algebra, right? Did you guys take a course on linear algebra? Huh? So what is a basis function? I think it's important. Remember I said that that's what is learning versus, yeah. So I'm positive, did you take with a math professor or an engineering professor? Oh, that's different. But that's how it is. But I'm asking what it is. Let's say you have a matrix, 2 by 2 matrix. Okay? There also we talk about bases. Either the columns or the rows form basis, or it has to be, you know, remember the unit basis, usually it starts with it, 0, 1, 1, 0. So the basis is very important. Take a look at it. Go back to your math algebra book. See, that's what is missing. This is a problem with Indian education system. Yeah. This is the problem. I'm telling you. Even IITs. Yeah. So I went to Kanpur. You know, Behra's group, right? This is a robotics group. You know, he's pretty good and all that. I have very high respect. So they didn't know all this neural network I was going through. I offered a few classes. Man, you should see. They were so happy that how this is the neural network. Yeah. So I think my suggestion is take a math book on linear algebra. Look at it. So in order for a matrix inverse to exist, we also say the rows or the columns of a matrix has to be linearly independent. Have you heard of that saying? Yeah. So that means that each of the row or a column has to span a particular direction. Those are your unit bases. So in a nonlinear function, like a polynomial, for example, or when you are expanding e to the power of x. So if you take my course on 5000 level, which is undergraduate students take, I explain all this. This is the fundamental difference. So e to the power of x. Remember, we did all those expansions when we were in high school. So e to the power of x. How do we expand that? Is a plus or a minus? X So you can write this, you see those constants, you see that x square. So you can actually write this constant 1, then 1 over factorial 2. This is your theta. Then your basis basically becomes 1, right? This is also x square, x cube. So this basically becomes your basis. And this is your constant. So what I mean is, we do all this, and Indian education system only gives you how to solve it, but doesn't explain it. So where does it hurt us badly is when we have to come up with something different. We don't know. Unfortunate, this except Aryabhatta and there are a few other eminent people like Ramanujan and others, we have a problem, right? Yeah, we are smart, but we don't learn. This is the issue with education, yeah. So this is, so the linear, we do deal with the linear, you know, the vector, the rows and columns. Basically, those are linearly independent. That means they have to form a basis. And unless they form a basis, you can't invert that matrix. And there are real, basis means those are the basic stuff to construct that e to the power of x. You know? So any case, so this is the activation function. In order for this f of x to approximate it, that activation function should form a basis. And sometimes it's very difficult to come up with a basis. So there are so many basis functions, splines, trigonometric functions, polynomials, okay, sine, cosine, all those, they all form a basis functions. And if you remember, you take a physical system and you derive the dynamics, many times the dynamics are given in terms of trigonometric functions. So the goal was, you need to have that in the neural network, then you're adjusting the weights, it becomes a traditional adaptive control problem. But the big thing is, you are relaxing the LIP even for a single layer network, and the two-layer network relaxes everything. Okay, so here is the two-layer network. This is called the input to hidden layer, then the hidden to the output layer W. Okay, so you feed the inputs x, the vector, it approximates it. So you have 1, 2, and 3, and so there are L neurons, and you get the outputs y up to ym. This is a very simple, basic things of a neural network, okay? So we use neural networks to approximate nonlinear functions. Remember that. So when the system is nonlinear, we are basically using neural networks. Remember I said one for approximating the value function, because in a linear system it becomes x transpose p times x. And P is the kernel matrix. You don't know P, so you have to solve the Riccati equation. So instead, we use a neural network to approximate V. We use another neural network to compute the control policy, because the control policy needs B or a G, and therefore you don't know G, therefore you can't solve the optimal control policy. You use a second neural network. It's called actor neural network. So you need two neural networks, but then you need to know how to adjust those weights and show stability. That's what's been challenged all along. So you see that two-layer network, I wrote those equations here. So you have, in a neural network, you have the input, you have a bias. And a lot of times you don't know the bias values. You put the bias as the first column of the weight matrix, then basically it becomes, you see that you can write it as ZL, and you write it much more simplified. And what you're doing is you're taking that WI0 and you are putting it as part of this, and you are adjusting it as if you don't know those values, because you don't know really. So those are WI0, those are called the biases. And the WIL or WLJ are called the weights. Okay? So the idea was, you need to adjust VLJ, WIL, VL0, WI0, and that becomes an adaptive control problem. Okay? So this is the output of a two-layer network. Y equal to sigma, that is the hidden layer activation function, V transpose times X, that is the input to the hidden layer, and sigma of that becomes the input to the output layer, W transpose, that becomes Y. Y is the output. So that equation pops up from this block diagram. You can see you have the X multiplies by V transpose X, goes through the sigma activation function, and then that goes as input to the second layer, W transpose sigma of this, and it goes through the output. Typically the output for function approximation, the activation function for the output layer is linear. We use a linear activation function. For successful approximation, there is a theorem called Stone-Weierstrass theorem. And what it says is, you can approximate any nonlinear function over a compact set, okay, by using a three-layer network with arbitrary number of neurons. When you say arbitrary number of neurons, you have so many weights and activation functions. This was done by Weierstrass sometime in early 20th century. He's a mathematician. So all of us use that theorem basically. And what it says is, you can take any function in a compact set and you can approximate it. Okay? So this is what we do, and that's why we use it in actor critique. So in the introduction to RL, I have that. Let's go back to that file now. And this is the last slide here. Okay, so let me pull up that slides, then you look at it, then you can ask me questions. I'm positive many of you will have questions. So we are missing one more lecture, isn't it? Or we are, I think the introduction to linear NCS. We are behind. Huh. No, we have to catch up. We cannot just back off. So you see this block diagram here. You see here you can see the critique. Critique approximates the Bellman equation, V, and the actor computes the control policy. So you have two neural networks. All right. So you can also see that so I'm using an identifier to approximate f and g. Okay, once I get the f and g, I'm using, this is the controller. So I'm using, you can see the critique neural network approximate the value function. The identifier provides the f hat and the g hat from adaptive control, and that information is used as the Hamiltonian, and that Hamiltonian is used to adjust the weights of the critique neural network. Then you see that this is the terminal constraint for finite horizon. I'm using that information back into actor neural network. See that the actor approximates it. Otherwise you have to take the derivative of the critique. You know, you have the g hat which is coming from the identifier. So you use the g hat, you take the gradient of this critique neural network, and you get the optimal control policy. So go back on these slides, look at it carefully what that means. And you see this, the identifier, output of the identifier is what? F hat and g hat. F hat is the estimate of f, g hat is the estimate of g. And these update laws, this is the update law for the weights. So here we are using two neural networks, one for identifier, one for the critique. So you can also do the same controller design. Instead of an identifier, you can have a critique network. There is also an actor which is a neuron, then you don't need G. So a lot of different ways you can do the same. Right. So the identifier basically uses a neural network. The reason is the identifier, we are assuming the states are measurable. Typically, identifier, you can assume that the outputs are measurable. And you can estimate the states as well as the dynamics. You can do both. So here, we are assuming that the identifier, okay, is basically estimating the states. This is how you compare, whether you are able to. So you can see that I'm writing x dot equal to f of x plus g of x times u. I am writing as two different elements, but it's the same neural network. So I can put it like a matrix form, and I can have one neural network approximating a big network, and then I am going to split that, one for f, one for g. Okay? So here you see that x tilde dot, x tilde is x dot minus x hat dot. I'm assuming this is measurable. But in many cases, the state vector is not measurable. So you use the output y, and you compute the y tilde, and use the y tilde to adjust the weights. So in this case, I'm using x tilde. You see that? This x tilde, so I'm adjusting the weights by using x tilde, which measured quantity. Okay, so the identifier in this case is giving you f and g, the estimate of f and g. Okay? Right, the system has to be observable. That is correct. The system has to be observable. So that's an assumption we make. So here is the robotic system simulation results, and you can show that it converges, and you have the identifier errors also converge to 0. It's using neural networks, okay? And you can extend it. So here is the paper. I was telling you the paper you guys asked me. This is the paper that the discrete time. I think she's not watching. That's your paper that. Okay, but you can pay a little attention here because you asked me the paper. So that's the one, that first one. The one that you guys ran intro to RL, discrete time, and that's the paper. So if you have a copy of that paper, you can actually see those equations and examples. Yeah. So there you see that we are using, here is the residual error or the temporal difference error. That E. And then how you construct that, and here is the block diagram. Example 1 and example 2. Yeah, there are examples here, yeah. Okay. So I think we are behind by one lecture. What do we do? Because today afternoon is tutorial. Huh? Oh, no, maybe today afternoon is a lecture. Okay, so maybe you are okay. I was worried. Right. No, I think I was worried, but let's see, because the afternoon is the NCS part. Yeah. Right. I know. That's what I'm doing actually. This is not how I teach, but there's nothing I can do. Okay. No, but that's a real problem, right? When you have two people, if you are married, you'll know that issue. So it's basically a multi-agent problem. a real multi-agent. So any case, okay, any questions here? Yeah. Right. The U. Yeah, because the you need the G. So that is one way. Let me say this. The other way is what I showed you. I can use an identifier and then one neural network for the identifier, the other one for the cost function. And I take the derivative of the cost function to compute the control input. And I use the identifier G hat in there. So that's two different ways of doing the same. Okay, what's your question? It's just a function. Cost function V has to be bounded, right? Remember that. So since it's a bounded function, we assume it belongs to some compact set. It's smooth. It's usually smooth. And therefore what we do is we say that since I don't know V, I'm going to approximate it, but I know the input. Usually it's X. And so I use a neural network and I basically approximate, yeah. So neural networks are used to approximate it. So what you do is, depending on I forgot to tell you there, remember you e to the power of x expansion. So I can write it now. I think that's a good question actually. If you have not taken a course on neural network. So remember, we looked at, so you remember, e to the power of x. So we wrote it as 1 plus x square over factorial 2 plus x cube over 3, and it goes all the way to infinity. So what a neural network is doing is, it basically, trying to compute these are the weights, and you see that x square, x cube. Now, depending on the number of neurons, you have the number of terms here depend on the number of neurons. That's what is approximation. So if I want to only use a linear approximation, then I take 1 plus x. You see? And if I want to do quadratic, I take, that's an approximation. That means the other terms, I'm just simply ignoring it. You see? That's what a neural network does. So the number of terms you can pull out is based on the number of hidden layer neurons. The more neurons you have, the more terms in the expansion you are able to approximate it. Got it? Okay. Any other questions, guys? Okay. Right. So you remember when we do task, we typically do in a finite time or infinite time. So sometimes there's a gray area. So some people say that 10 seconds could be a long time. It depends on the process. So one way to look at it is the time constant of the system. If it's a nonlinear system, there's no time constant, but actually you can look at the response. So if the system has a very high time, very high time constant, that means it decays much faster, right? So in those instances, you really want to do as a finite time. So, but you can also look at it in a different way. Let's say you're setting a temperature in a room, that's infinite horizon. Basically, you set it, you want the temperature to stay. Whereas if a robot is picking up objects, let's say it picks up something and moves and then it places it, or a robot tries to do some operation, those are finite time, because it has to do drill a hole. And if you look at it, it drills a hole, but the time is maybe 5 minutes, and those are basically, so in general, most of the tasks we do are finite horizon. But we formulate it as sometimes infinite horizon because there are a lot of things get simplified. that there is no terminal constraint, all that stuff gets wiped out in the infinite horizon. So we like it, infinite horizon, but because in infinite horizon you saw that the Riccati equation becomes algebraic Riccati equation, so all those becomes constant, it reaches a steady state, the gains will become a steady state value. So there are a lot of benefits to simplify that, rather than making it time varying. So this is basically why. So it depends on the process. Sometimes some process converge very quickly, and so you can actually pose it as a long, infinite horizon. In sometimes the process is so slow that you really need to pose it as a finite horizon. Yeah. What else? Yeah. Yeah. Right. No, I think you need to first pose the problem as an optimal control problem. There are papers, yesterday we talked about it, the Paddy's advisor. There are papers by Paddy's advisor, not Paddy, maybe Paddy might have it. But to look at Paddy's advisor, Balakrishnan, he passed away recently. He has done a lot of papers on path planning. So you are formulating the path planning problem as an optimal control problem. It's a formulation issue. But once you formulate it, the solution is the same. Right. So that's always a challenge. Because here, if you remember in the reinforcement learning, never talked about exploration and exploitation. Remember, why? Because in real-time control, I'm not doing any offline training. Remember that the weights in neural network. I'm doing everything in an online learning. So that's a good question. So since in adaptive control, we normally don't do any training at all. In neural networks, people talk about training and all that. Now, we can't use training in control. Why? That's a good question. Because if you look at what the computer science people do, when they train a function, they need what? I mentioned this. They need what? Data. To do, the data is called what? I did mention that. Well, people call that, but it's called targets. So targets are the desired values. So what you do is, that's what is training. You feed them inputs, you find out the output of the network, you have a target for that value of the input, you compare that, and that's the error. And there's a method called backpropagation. It takes the error and it propagates through the network. Now, why is that backpropagation became very famous? Because if you remember, the hidden layers don't have the targets. It's very difficult, only the output layer. So that propagation method, essentially using chain rule, we won't have time if you take my neural network class. So that basically gives you a way to come up with the targets. That's why they became very famous. And that's the only thing they use pretty much in everywhere. LLMs, everybody. But in control applications, we can't use it. So the method that I developed in '94 for multi-layer is called direct error driven learning, where you use the error directly in each of those layers. And you can show stability. It works magically better than the well-celebrated backpropagation. Okay, so you need the targets. And for control, many applications, like in this case, FNG, I don't have targets. I don't. You find out how you can get targets. You have to really play. You don't have targets. So if you don't have targets, you can't use the conventional method. So then you have to use the Lyapunov-based method. You see, that's where we call that as online learning, the real-time learning, basically. All the control people use that because you cannot take a chance saying that, oh, I need this much data and all that. There are a lot of problems with that approach. Yeah. So if you have done some neural networks, these are some challenges that you will face. You see? See what I'm saying? So we don't use, in control, we don't use supervised learning. And in reinforcement learning, I'm not using any targets. You see that? So I'm not using the to coming to the question, there is a way to accommodate exploration. It's called replay buffer. I don't want to talk about it today because that's a whole lot of problems, issues, and there are papers that we are working on. If you look at more recent papers of mine, it talks about replay buffers and all that, where we do the exploration and also exploitation. So yeah, we won't have time. Otherwise, you won't be going for lunch. It's already 10 after 12. You see? Got it? It's a lot of this. So a lot of stuff has been happened. Yeah. This is why I keep telling you, don't go out without learning these guys. Because remember, I survived. And you know what? I thank my advisor. Honestly. And every student of mine is so successful. So it's very important when you graduate, you have the right skill. Not now. Don't go out thinking that you should be good now. In 5 years and 20 years, you should be able to survive. Remember that. Things change so fast. So to answer your question, there are so many papers. You email me, I'll send you some papers. So they call replay buffers and all. I'm not even covering that because we didn't use it for NCS. There are a lot of different things that comes more into advanced oral topics. You know what I'm saying? So you could do that. I'm not covering it, no time. Okay? So look at papers by Balakrishnan. He did a lot of re-entry vehicles. There was a lot of stuff. Yeah. So that is Dr. Padi's advisor. Maybe he may be doing now. He still does adaptive critic stuff. Yeah. Huh? I think we should stop, right? Because otherwise we won't be able to come back at 2 o'clock. Yeah. That's why I kind of cut that question, unfortunately. Because that's another big stuff, to explain this. Okay? Okay, so one of the questions before I think we left for lunch, that how is this exploration thing comes in. So I just thought very quickly give you a little with a very high level. Okay, so if you look at this example, if you see this example, so you have a nonlinear system, and here we omitted all the activation functions. You pick a stabilizing control. So this has to be admissible. Remember I said that admissibility is more important than stabilizing. And then, you are comparing online with offline, because we want to see whether you could do that. So if you look at this, so here is the actor critique weights. You can see that the weights are kind of moving around, and then after that they converge. So the question is, where is the exploration? That's what your question was. So you can see this here, as the state is trying to converge, you put noise and then you perturb the state. Okay, so that's one way of exploration. So why do we do that? So if you have taken adaptive control course, so how many of you heard of this persistency of excitation? Yeah, so there's only one that says raising his hand. So persistency of excitation is a condition that's called PE. So this is a very physics-based condition. Basically, if I really need to understand what is inside the system, think about the system as a black box. I need to know what is inside the system. So what do? I basically, it's not just I apply a signal in the input, and I don't expect that whatever is inside that box will show up as the output. That only happens when the input signal is called persistently exciting. So what does it mean? It means that your signal has to cover mathematically n dimensions. It has to basically span, so that you are exciting what we call all the modes of the system which is inside that black box. Okay, so think about this. Let's say you apply some signal. Let's say you have a blade, you're holding the blade on one hand and you're moving it. So what happens is you get some sort of a vibration, but you do a little differently, you get a different set of vibrations. Now those vibrations provide you with certain harmonics. Okay, and those harmonics you can add them up to become a series. So there are what we call, those are modes, basically basic things that are representative of the physical system inside that black box. So if the input is not persistently exciting, that means you are not exciting all the modes of that black box. As a consequence, you don't see those terms appearing as the output, in the output. So what will happen if you don't see it? You don't know that the actual behavior of the system. You see? So a good example is, like you probably heard, right? When they design bridges, they look at the load and all that. There's a reason, right? Because when army marches a bridge, it happened before. The army's marching synchronized with the oscillations of the bridge. Okay, and when that input actually is going and colliding with the actual oscillations of the bridge, that blows up and things have collapsed. Resonance. So the idea was, if you have understood those modes, then you can actually look at what type of signals you should apply or not to apply. Okay, so for identification, if I want to identify what is inside the black box, I need to have that input signal to be persistently exciting. Why? What is identification? That means I'm trying to learn the behavior of the system. So if I'm not applying that signal which is persistently exciting, I will get a completely different system that is not representative of the black box. That's the main issue. Okay, it has a condition. It's very difficult to either verify or guarantee the PE. But there are ways you can do it. One of them is just the noise. You put a random noise, and what you do is you're trying to perturb the system, and by doing that you're expecting that the modes will be displayed as part of the output. Okay, so here you can see that's called probing noise, and a lot of times we use probing signal. So this is a probing noise you're putting on the top of the control input, and then you are removing it after some time. Okay, so by doing this, basically you are saying that the signal will be persistently exciting. Okay, so you can see because of that, you see that the state vector is getting close to 0 now, and you are pushing the system back away from it. So by doing that, you are exploring. Otherwise, if it converges, those set of weights are probably may not be representative of the entire region of operation of the system. So by pushing the state vector away from 0, you are kind of creating different initial conditions, and then you are trying to learn. So that's basically a form of exploration. So once you do that, then you remove the PE signal out, because you already explored, you see? And then those set of weights that converge would be the best set of weights. You see what I'm saying? So that's one way to do it. Okay? So you do require this. So you can see that we compared offline versus online, because the offline solution is much more computationally intensive solution. I really want to see. So this is online, and you see that initially there is some error. Eventually it converges to 0. So that shows that the online control, and here is the online offline. You see, this is x1 versus x2. This is the path. They're very close. You see, that shows that the method that you are using, in this case the controller, is really doing a good job. Okay. All right. So any other questions, guys, before we start the new chapter? Any other questions? Okay, so let's go into uncertain and LCS. This is lecture 3 and 4. So 3, that's what we are doing now. So optimal adaptive control of uncertain linear network control systems. So remember, uncertain means the dynamics are not known. Remember, we have been talking about that. The A and B, this is a linear. Therefore, here I'm talking about the AZK and BZK. Okay. So here you can see there is a difference between finite horizon, infinite horizon. If it's a finite horizon, basically you have a terminal constraint with a weighting function S subscript n. N is the number of sample instance. And this constraint is not equal to 0. If it is infinite horizon, basically this constraint becomes 0. Okay, that's the difference. So solution of the HJB equation, or we call Riccati equation, if it's a finite horizon, this is a time varying KK. If it is infinite horizon, this becomes a constant solution, which becomes algebraic Riccati equation. Okay. So again, to recap, so this is a constant A and B. This is x of k plus 1. Here is the cos function. This is the terminal cos function. This is from k to n minus 1. This is n. This is n minus 1. This is quadratic. Okay, and the goal is to minimize this. So in order to minimize it, so here is the Riccati equation. I skipped the steps. You see, the Riccati equation needs a solution which is s of k plus 1. S of k plus 1, or this is the s of k. So this is a recursive equation also. And once you get s, you plug it in. The constant k is given by this. It requires b and also a. Okay, and so without a and b, you can't compute the optimal gains. Even with a and b constant, the optimal gain is time varying, kk. Okay, it's time varying. So this is what we talked about. Okay, So I'm trying to do that. But the drawback, like we said, this is backward in time. You have to solve this Riccati equation from backwards, and the system dynamics are required. Otherwise, you can't solve it. Okay? So if it's a nonlinear system, because this also covers nonlinear, so we did that. Here is the value function. You're trying to minimize u of k. Here is the control policy. So this is the system description, and then you get the continuous HJB equation instead of Riccati equation. Use the solution of that. The solution of the HJB equation is V star. We use the V here to obtain the U star. Now, if you look at the U star, in order to compute U star, you need the G. Okay? You need the G. And in order to compute the HJB equation, you need both F and G. The same issue. Okay? And so, remember, even if it's not NCS, in order to relax it, you can use one neural network to approximate that. And you can use another neural network to approximate the solution of this using reinforcement learning. So that's where you have two neural networks. Either use identifier, or if you don't use identifier, you need two neural networks. And that framework, we used to call that as actor critique framework. That's what we have been doing there. Okay? But the HJB equation, there's no closed form solution, even if you know F and G. So therefore, you use approximate way to solve it. And that's why we use neural networks. Numerical ways. Okay, so I'll skip that. And the only motivation we have, so you see this guy, Balakrishnan, he is the aerospace guy. So he was doing even before us optimal control. He's known for optimal control. He's the Paddy's advisor. Yeah, aerospace. Okay, and you can see this was in 2011 using single network adaptive critique. In fact, Paddy keeps using this. Okay, all right. So the motivation was an online means real time. Okay, forward in time algorithm without performance iteration. And I told you the iterations, we have problems because we don't know how many iterations to use. And where do we use the iterations, guys? Where do we use iterations? In here, where do we use the iteration? Where do we need iterations? I know the intro to RL, there is one of the code uses the iteration method. And the other one uses without iterations. That's the traditional adaptive control. So why do we need iterations here? What does it mean by iterations? The iterations are mainly to solve the HJB equation or Riccati equation. Because there is no closed form solution, you need the solution of the Riccati or the HJB equation. So basically you're holding the time and you're iterating it. That's what we do it in, if you have taken a numerical analysis course, you create a mesh and you hold at one point and then you basically iterate till it converges. Yeah, so when you say converges means you take the value, that's the solution of that, you check the value function of I, and you minus the value function at I minus 1, the previous iteration. If that difference is less than some epsilon, then you think that the solution has converged. So that is the numerical solution or a way to find the solution to that HJB equation. Right, it's very similar, but it's not exact. Yeah. So, but it's very similar because that's how you pose your problem in LMIs. But here, actually, because that equation essentially is a nonlinear equation and it doesn't have any solution, and then so therefore you start with, we did the undergraduate numerical methods where you start with initial value and you basically iterate it till it converges, and then you basically you have a mesh then you x equal to x plus x naught, then you go to the next step, and then you do the same. Yeah. And that's probably the best solution you get if it converges. But the problem, I think, is, as I said, if you have a time, because in control we use time, and so you have to apply control inputs at sampling instance. So the issue comes in is, well, within that sampling instant, can you have, can you do like how many iterations can you do? And if you don't do enough iterations, the solution may not converge, and if the solution doesn't converge, things will blow up. Okay? All right. So this is the state feedback A and B matrices. We have seen that. So now here Q function. Remember, so this is a linear system. I'm going to use Q learning. So how do I do that with dynamic programming? So you see this. This is the Bellman equation. R plus jk plus 1, right? This is the j of k. So this is my Q function. I can write these two as in this form, where in x of k, u of k transpose some matrix G multiply x of k, u of k. So this is actually equal to that. There's no, confusion. It's just you can write it in that form. Okay? So that took a while for us. So what is G? G is basically given by Q plus A transpose this. This is the second term, this is the third term, and that's the fourth term. It's a matrix, right? So this is scalar. This is scalar. So this is transpose matrix, a vector. So if you multiply this, the dimension should match. Okay? So now you can see that in order to compute the gain k, kk, I take this inverse of that, multiply by that. So that's basically what is here. See, inverse of that term, multiply by that term, this is my kk, which is exactly inverse of this, multiply by that, is my kk. Okay? But remember we said, in order to use this, I need B, I need A, I also need the solution of this, which is the Riccati equation. So now what I'm doing is, I'm going to pose this problem as an adaptive control problem with using your reinforcement learning. That's what I'm doing. So how do I do that? Basically what I do is, this is the Q function. I'm going to call this equation as a Bellman equation. I'm going to drive this equal to 0 or some small value, right? And then this is like a temporal difference error. So here is what I'm doing. This Q function, zk transpose G matrix times zk. So I'm using Kronecker product because I want to pull this outside this matrix here. This matrix, I want to pull it out. In order to pull it out, mathematically we call that as a Kronecker operator. Okay? So otherwise you can pull it out. So you can see this gk, this one is like a vector. You take each column and you put it like a stacked. You stack it. The whole matrix is stacked. And then this basically the z bar is basically, you see this is z bar is basically an expansion of regression functions. Okay? So you can do that. Once you have done it, then basically you can try it out. You see that? Then V hat is Q hat is G hat, this is unknown parameter, this is the known basis function, which is this times that times G bar, which is given by that. So this becomes adaptive control because I don't know this, I know that. So now what I do, I use this Bellman error, which is E of k plus 1 equal to Q hat at k plus 1 and Q hat at k plus this. And this difference is called temporal difference error. You see? In reinforcement learning. So R is you remember I said R is basically k to k plus 1. Yeah, in the infinite sum. So remember, you can expand that k to k plus 1 plus k plus 1 to infinity. In this case, is a finite horizon. till n minus k. You see that this is a finite horizon, n minus k. So n is my final time. Okay. So then you also have a terminal constraint error. Because this is a finite horizon, you have a terminal constraint error which is g hat and g, so you can write it like this. So this becomes like a traditional adaptive control problem with the measured Bellman error. So you're measuring the Bellman error. So the Bellman error is used now to adjust theta hat, which is the unknown parameters. Okay? So that's what this update law is. The theta hat of k plus 1 is, this is bunch of data, alpha this minus that, and here are the expressions. So you are collecting the values at each sampling instant. And then you are building that using least squares, method of least squares. So this update law is basically a method of least squares. This theta hat is nothing but that theta hat. So that theta hat would give you the solution to the Bellman equation, and using that we compute the Kalman gain. Okay? So remember this theta hat is same as the g hat transpose. And what is g hat? G hat is the matrix, that capital G. You see? So basically you're taking the matrix and you're converting into a vector which is g hat. Then you're estimating the g hat using adaptive control. Then basically you are taking the vector and you are redoing it as a matrix capital G, which is given here. Okay, so you see that capital G, G of k. And then what you're doing is you take the bottom row, take that diagonal element, you take the inverse of that, and you multiply by the first bottom element, and that gives you the kk. Okay, any questions here, guys? I want to make sure you understand this, because we're going to repeat this for linear system. Any questions here? Okay, so this is you can see that this is finite horizon, right? This horizon is finite because n minus 1. Okay, this is not infinity. Because of n minus 1, this is k, I equal to 0 or I equal to k to n minus 1. So this is the n minus 1 terms, this is the nth term, which is the terminal state. This is called terminal state, okay? So there is a constraint. So for example, you're parking a car. I don't know whether you drive a car. So the car can have coordinates x, y, and z, right? But there is an additional one. The additional one is the orientation. So I can park the car perpendicular or just 90 degrees. I can, the same location, I can turn the car like this. So x, y, z is the same, but the orientation of the car is 180 degrees. So that terminal constraint essentially dictates what is the terminal state of the system, how you want it. Okay, so you have to satisfy both. You have to satisfy that and you have to satisfy this. Typically, if it's infinite horizon, this term is 0. That term is 0. Okay, so you can see that what's going on here. So that's one thing. The way you define the error, you see, this is the Bellman error. So this Bellman error is basically from that equation, that k plus 1 and k. So this is called difference in time, the value of q hat at k plus 1, the value of q hat at k. And how did we get that? Remember I showed you that v of k plus 1, remember I take that v of k equal to that r of k, that is where the k to k plus 1 plus v of k plus 1. V of k plus 1 is k plus 1 to infinity or whatever. Then you move that v of k to the right hand side and you get a 0. And instead of 0, we call that as a Bellman error. And that's same as e of k plus 1. We call that e of k plus 1 as also as temporal difference error in our reinforcement learning. The same. Okay, so since it's a finite horizon, you also have to have another error, which is the terminal constraint error. No, this error is 0 if it's infinite horizon. So g hat of k comma n minus gn. So that's this minus that. So we know this, we don't know this, we want to find out. So this theta hat here should also satisfy that when you are trying to find. So you have two errors, you are trying to minimize both the errors at the same time. Okay? So here is the update law. Now, there is a little more involved in here, which I think I'm skipping this, because you really need to know how you're solving the math and how do you show the proof. Those are in the papers. Yeah. So this is the theta hat. That's the least squares approach, how you get the theta hat. And if you use the theta hat, you can show that the parameters converge. Theta hat converges to theta, the target values. You don't need the target values, but you assume that there exists a target value. That's what in adaptive control we do that. Okay? Any other questions, guys? Any other questions? So you see how I formulated that. So originally we took that matrix. We need to construct the matrix. So that gk xx, gk xu, gk ux, gk uu, and the k, that the Kalman gain kk essentially is gk uu, which is the second row, the last element. That is the inverse of that multiplied by the gk ux, the first element. So at every instant of time, I reconstruct the gk, and then what do? I take that gk uu, inverse that and multiply by the first element. That gives me the gain. So by doing this, I am able to overcome, I am able to avoid the need for A and B. You see? Any other questions? So this is how the dynamic programming, the reinforcement learning, they're all coming together. So because of reinforcement learning, we are able to relax the need for the system dynamics. So my question is, or if you ask me, can it work for any A and B? Yeah. So this type of controllers, we call that as universal controllers. So this is always, we are after that. Yeah. And here the KK is optimal. This is an optimal gain. When you say optimal, that means it minimizes the cost function. So you want to use the cost function as a comparison. If you want to compare two controllers, you define a cost function and you see which controller gives you the minimum cost. Okay? Any other questions? Okay. So here are some mathematical results. You see that theorem 1 shows the bounds on the parameter estimation error. So you see that the initial value is bounded. U0 is an initial admissible control. Remember I said that what is initial admissible control? Policy. And then you see that let update law for tuning theta hat is given by that equation. Then you say that there exists a positive constant learning rate, alpha. That alpha has to be within 0 and square root of half, such that the estimation errors are all uniformly ultimately bounded. And then we show the proof. Theorem 2 shows the boundedness of the closed loop system. So theoretically we show everything is converging, everything is bounded. Now that's the state feedback. Okay, so we can also do the output feedback. Now remember, somebody asked me, I think he just stepped out. So observability. Remember I said controllability is one thing and what is observability. So anybody had looked at what is the Google, I asked you to Google and find out. So the same thing, what is observability? What is meaning of that in a physical term? What is the meaning? That's right, but that's what is observability is. So that means that if I have a black box, think about, remember I keep saying that the black box is my system and my outputs are coming out. So what I'm seeing is I'm seeing that on one end of the output and I'm seeing what is going on inside that black box. Okay? So that's observability. So if you remember, somebody who studied human stomach. I don't know if you realize this is true. One of the physicians, apparently one of the patients had a hole in the stomach. This was, I think, 17th century. So he was able to observe when the food is eaten, he was able to see what's going on inside the stomach. This is what has been done in 17th century. So if you read it, you will know. Okay? So here, basically that black box, the outputs are the things that are coming in. Now, you probably have seen kaleidoscopes. And when you are a child, right, you know what kaleidoscope is, right? There's 3 mirrors and then you put something and you rotate, it forms a lot of patterns, right? So what do? You are watching that through a scope and you are trying to see what is happening inside. You see? So observability actually shows that whether you could see what is cooking inside that black box through the outputs. Now, remember I said that, learning thing. And I'm not going to answer that, you're going to find out, okay, and tell me. So what happens when the process is not observable? So what does it mean? Because you need to know that. You know, like you said, everybody explains that observability means you have to observe the states of the system through the output. That's no big deal. But suppose a system is not observable. What do you do to make it observable? I think that's important. I'm telling you, a lot of people don't know even that. Faculty. What do you do? So if you ask a person in the industry, he will tell you, not from the academics. So academics usually knows how to test the controllability, observability, that matrix stuff. But essentially, let's say your system has a problem. And you know why? Because what happens is, usually the mechanical guys design something, right? And they just say, okay, electrical guys, the control guys, you're going to do the control. And if you work in the industry, big companies like Boeing or Caterpillar or any of those companies, there'll be a separate group doing the control. There's a separate group that is designing the physical system. Always, okay? So they don't care about controllability and observability. They just design for their own specifications, right? They have certain performance indices. And the controller guys will sit there and have to break their head because sometimes the system may not be controllable. So if the system is not controllable, there's a meaning for it. You can't sit there and do the math and say, well, I can test it. It doesn't work like that. Because they don't care. They'll say this is the best. So a good example is engine. Okay, let's say you have an engine, and the engine, remember that an engine is explained like very simple, okay? Engine is what? Let's say if you are driving an automotive car, you have a 4-cylinder or 6-cylinder engine, for example. Have you heard of that? So you guys take any course, like most of you are AA. Do you take a course on thermodynamics or anything now? No. Right? No. Okay, now, no, nothing. Now they pass them. You don't need to know anything, right? So, no, I'm serious. This is the damaging thing, right? So, very simple layman's language is engine is like a kind of a cylinder with a piston going up and down. Okay, very simple, right? So, what happens is there's a valve, which you call inlet valve on one end. There is a valve at the other side of the cylinder called exhaust valve. So, always one of the valves is open. Okay, so what happens is that one end of the piston, there is a piston on, which goes inside. The other end of the piston is connected to what they call crank. It's like it converts the linear motion into a rotary motion. That's basically what that is. Very simple, right? So one of the valves opens, it takes air, you put the fuel. Sometimes you have to burn the fuel. There's a spark. In some cases, you compress it, and that basically creates a spark. Okay, so what happens is once it creates, it expands, so the piston moves up. And as it moves up and down because of this energy, basically the car rotates, the rotary motion basically becomes the linear motion. Very simple. You see, that has to be that simple, you have to explain. So those days, we have to study. But you remember I told you when I learned all this during my research. Yeah. So if you don't do research, you're no good. So that's a very simple explanation. So you have 4 cylinders. Each cylinder is basically split at about 720 degrees. So one of them will go up and down, then the other one will do, then the third one. So basically what happened, constantly that thing will be rotating, because at least one of the cylinders get fired and it expands. This is how your cars move, okay? Any of those vehicles, most vehicles. So if it's a 6-cylinder, and then you divide the time 720 degrees by 6. Or if it is 4 cylinders, you take 720 divided by 4. So 360 is one rotation, right? I hope you guys are clear about that. So we use 2 rotations, 720 degrees. Yeah. Okay. So remember, you got to have that. So if you don't have interdisciplinary background, so as I said, he's doing control. So control, there will be one group. There will be people who are designing engines and all that. They'll be sitting in a different group. And they never talk to each other. Never talk to each other. So one group does the design, and they do like how to minimize the thermal efficiency, all that, right? Waste and all. And then they design something and they'll give it to the control people. Usually the control people are the doubly guys who have no clue. Now I think you probably don't even have a clue. I'm serious. I have done that in Caterpillar when I was doing it. Yeah. So that concerns me. So the controller, so here I asked this question, why? Because then you know what happens, many times the guys in mechanical, they don't understand what is controllability, what is observability. Then the controller guys have to do that. So when you talk about observability, it has to do something with sensors. I'll give you a little hint. When you do the controllability, you do with actuators. So find out what is the physical meaning of controllability and observability. And what happens suppose the system is not controllable. And you're going to find that. You see? So you can't go and say that my matrix is not working or something. In most cases in engines and all, there's no mathematical models for the dynamics. Okay, so here is the observability. So observer, you have an observer, you're assuming it's observable. Observability, controllability is, how do you test the controllability for a linear system? What is the equation? So controllability is always with A and B matrix. So B, A square B up to A into the n minus 1B, right? So what is the observability? C, CA, or C, CA, whatever, But that we know, but we don't know what it means. So that's a danger, serious. Yeah. So you have to produce engineers, but not mathematicians, remember that. You need to know the mathematics, but as an instructor, you got to teach engineering, not the mathematics. So they know what happens. Yeah. So that's why we import, right? In India, pretty much everything gets imported. I don't know, I think I shouldn't say this, but one of the attendees, he was saying they build all these things. But you know what? I've seen most places I visited, they just import everything. Missiles, everything from outside. Yeah. This is very unfortunate. That's very unfortunate. We have very brilliant minds. All of them are in the US. Yeah. So, but I'm just saying that disconnect, that mathematics to the physical thing is what I'm asking you. What is the meaning of observability in a real situation? What is the meaning of controllability in the real situation? So what happens when you don't have that? Let's say you test it and it doesn't work, what do? See, that's very important. And if you're working in industry, it's your headache. Yeah. They'll tell you it's your headache. So mechanical guys, they do their design, like an engine, for example. They do that based on their own specs. and their goal was to minimize the losses, like heat losses and stuff. But it's your headache to design a controller for that engine so that you put in the fuel and it minimizes the fuel and it generates the amount of heat energy which is converted to the mechanical energy. That's your headache. But so the first thing you do is, how do I design a controller? So then you need to know what is controllability, what is observability. But what happens when that system is not observable? What do you do? Yeah. So I'm also a faculty, remember that. So you guys teach controls? Yeah, I think you should be careful. So if you want to really make a student, remember that, you really need to know that connection between the math and the physics. This applies to everybody. Okay, so I won't tell you that, and I want you guys to find out. And then there are a lot of brilliant minds here, faculty, so I thought I would let them go. So here is the output feedback. So we are using an observer. So that means that you only have the outputs measured, you don't have the states. Okay? So I still want to use the Q-learning. I still don't know A and B. Remember that. I still don't know A and B. So in this case, it's not network control system, just the, first let's understand this without network control. So I'm using an observer. Remember that A and B are assumed to be unknown. C is known. So here you can see, here is my observer. I'm estimating A. I'm also estimating B. So this also is unknown. So I'm adding yk minus c times, this is basically like a Leuenberger observer. Okay, standard Leuenberger observer. All right. So this L hat, you have to make sure that A hat minus L hat times C or whatever has to be observable. Okay, then you can actually find a L. So basically you convert this into error. This is the error equation, x of k plus 1 minus this, you get A minus LC times x tilde plus this. Now this term is basically A hat, B hat multiplied by x hat and UK. This is the basis, these two terms are unknown. So now you see that how I converted this into an adaptive control problem. So this is the unknown parameters, which basically has A hat and B hat. This basis functions is x hat and u, which you know. Okay, x is you don't know, but x hat you know. All right. So now what you do, you see that this term is A tilde, B tilde, and L tilde. These are unknown, and this psi is got x hat, u, and y tilde. We know y tilde, we know u. We also measure. We also know x hat because that's a mathematical equation. Okay. So this is how you formulate the problem. All right. Then you basically come up with an auxiliary error with some data. So you take the data from k minus 1 previous history. And the same thing you do that, you can write it like this, and here is the update law for the observer. If you update it like this, using this data, then actually you can show that everything converges, and the parameter estimation error, that is the target values which you don't have to, and the actual values, you are showing that they eventually become smaller and smaller and converges. Math using Lyapunov. Okay? So you can see, then you can use the Q estimator. On the top of it, this is the theta hat I showed you. This is the total error. Total error means the terminal constraint error plus the Bellman error. Remember, we had two. One is the Bellman error. You also have the terminal constraint error. So E total is basically the total of those two, sum of those two. So you use the same Q-learning using the output feedback. Okay? So you can see that here is the state feedback flow chart. This is the output feedback flow chart. So in the state feedback, you initialize the value function, you compute the Bellman equation, Bellman error, terminal constraint error, then you use the update law to update the parameter weights, then you basically unpack it so you get the G hat, then from the G hat you compute the optimal policy UK hat, and from UK hat you find whether you have reached the final time. If it's not, k equal to k plus 1 and you go back. K is the sampling instant. Okay? If it's an output feedback, you still initialize the cost function, U equal to initial admissible control, V naught equal to 0. You first update the observer, X hat, then you update the estimator, then you use the G hat, Q learning, and then once you get the Q learning, you check whether K equal to N, you reach the final time. If not, you go back. Okay? So that's the flow chart of state feedback versus the output feedback. So let's take an example, F16. So how many of you heard of F16s? So what is F16? I know he knows. So we also import, right? Pretty much everything. Mirage, everything we import. So what is F16? Huh? Fighter jet. So I know Trump was trying to offer F-35s, right? Yeah, that's more recent ones. So F-16. So this is the linear dynamics of an F-16 aircraft. Okay? So you can see that this is the A matrix, X, B matrix, U. So here is my cost function. So now my sampling interval is 0.1 seconds. Weighting matrix Q, R, and SN, they're all identity. Then we use the polynomial of time to go with saturation. The saturation is mainly not to let the basis functions to blow up, okay? So now you can see, I'm plotting here the system response, the states. The states converge. You see that goes to 0 for regulation. This is the control inputs. It goes to 0. And you see the cost function error. It goes to 0. And look at that. I have two errors. One is the Bellman error. Other one is the terminal constraint error. So what I want to show you is I show this. They all goes to 0. So when they go to 0, you know that's basically means that it is optimality. Yeah. Okay. So therefore we basically show that it's converging. It works. Okay. So that's the conclusion. Okay. So now we apply the same thing for the network control system. The only difference is in this example, I don't have a network inside the loop. Remember that. So if I put a network inside the loop, you guys have seen it. It becomes a AZK, which is ADK in this case, and then you have a BDK. These are stochastic and time varying. You see? But the process is identical. What you did. The Q-learning. We use the same Q-learning, except that it is basically that AZK, BZK has the random variables inside that. But it works. Okay? So, you know, these math equations are very scary, but it's not. Basically, this is a standard bunch of equations, like you're trying to minimize it. You have the E there, which is the expected value, because that is the stochastic. And you want to make sure that the average value reaches and is bounded. Okay? So that's it. That's it. So you see the R has got the XT, Q, XT plus. So all this is very sim. So here is the one of the constraints. This is the temporal difference. Okay, so the notations are different, so people scare you and write more papers, but it's the same thing. So here, this is the terminal constraint error. The second one, because this is a finite horizon, is equal to 0. And from there you get the optimal control, which is the E R inverse B times partial V star, where V star is the solution to the Bellman equation. If it's nonlinear, it becomes a JB equation. Okay, so all that derivation is there. Eventually, okay, so stochastic solution to the certainty equivalent SRE, stochastic Riccati equation. The reason is certainty equivalence is you're assuming that there is a process noise, and we're assuming those terms you don't care. And so it's a certainty equivalent of stochastic Riccati equation, and the control input evolves backwards because I'm not using Q-learning on this, right? And for finite horizon, the control gain becomes time varying. We already saw that, even in the standard case. So we really need forward in time solution, okay? So if it's a linear network control system, the system matrices are stochastic, time varying, and unknown. We already saw that. All right? And the disturbances and the process and measurement noise are considered absent, just to make sure it's simplified. Otherwise, it becomes more laborious. That's all it is. So here is now let's go to the network control systems. So there are two types of delays. One is the delay between the sensor and the controller. And there is other delay from the controller to the actuator. There are two sets of delays. Okay, so the sensor to control delay is kept less than one sampling interval. The sum of two delays is bounded while the initial state of the system is deterministic. This is a very standard assumption. Now, remember, if the delay is more than a sampling interval, what does it mean? So what does that mean? It becomes open loop. So that means that for two sampling instants, you don't have any feedback. And it becomes open loop. Sometimes the system can become unstable. Yeah. So you have to make some assumptions. So you can see that for a wide area network, two types of delays are considered independent, ergodic, and unknown, whereas their probability distribution functions are. So this is what I was saying. You don't know exactly the delays and packet losses, whereas you say that they belong to a distribution. Okay? So then you derive the dynamics. We have seen this. Okay, and then you get that AZK and BZK, and you can see that AZK has got that packet loss and then the delay. So we have seen this equation. Okay, and we also, I told you, if the original system is observable and controllable, then the network control system is also observable and controllable. Okay. Then we use the Q-learning. Because this is a linear system and we're going to use the Q-learning, the process is very same as what we did. So linear network is time varying and higher dimension because you are using an augmented system. So because of the augmented system, the AZK, this dimension of this matrix is different from the original system. Because you see that there is this vector, the ZK, essentially has XK previous values of the input all the way to D bar. So depending on how many values, delayed values of the input you take, that dimension of that vector changes. Because that changes, AZK has to be accommodating. So therefore, the dimension of that matrix AZK will be different. You see? Okay? So don't forget that. If the original linear time invariant system is controllable, then NCS is also controllable. We have proven that. That's in the first chapter. I skipped it, but you know. So you do this process is identical, I explained to you. Okay, so this is a finite horizon. We got to do a little more math. I'll show you. So if there exists a positive definite function L of the linear with strengthened condition that if this L of x of k plus 1 minus L of x of k, if it's less than or equal to minus of alpha times L. Now why is that minus is important? What does it mean by minus there? What does it mean? Yeah, it's the same as the differentiator. So L of x of k plus 1 minus L of x of k, if you divide it by the time interval t, that's your derivative. So what does it mean by L dot less than or equal to minus alpha times L? So the system energy is decreasing. The Lyapunov function is nothing but your energy. So how many of you guys read about Lyapunov stability? Huh? I see many of you nodding. So do you know much about Lyapunov, the guy who developed this method? Huh? Yeah. And you know, this guy is a very brilliant guy. I'll tell you something. This is a very good lesson. So you get excited. Look, this guy is so brilliant. Okay? Everything is energy. Nothing, you know, the Lyapunov stability is nothing but energy. Okay? And remember, we did that in high school. You know, energy can be neither be created nor destroyed. So it transforms from one energy to the other. So the Lyapunov stability basically takes some kinetic energy and potential energy bundled together. That's your total energy. And you're looking at how the energy is being dissipated. Right? And you know that when the energy becomes zero, just like a human, you basically become immobile, right? You just stop, right? You don't mobile. So that's your equilibrium point. Right? So that's what that is. So the minus sign basically shows is decreasing, and ultimately it just stops at some place where the energy becomes zero. Okay? So in terms of Lyapunov, this guy is so powerful. So the difficulty with any of the proofs is finding that Lyapunov function. So we spend a lot of time trying to find the Lyapunov function to show that the first difference becomes negative because that is decreasing. And you know what happened? He died before he told how to find that Lyapunov function. There are some things that people use, but those are basic, like quadratic functions, and you try to do that. But in a general system, it's basically, so it's a sufficient condition. That means that if you use a Lyapunov function, you prove it, it works. But if you cannot prove it, doesn't mean that the system is not unstable. That's the problem. And he passed away before he was able to tell the world how to do it. And it's been more than 100 years. Nobody is able to come up with a way to find it. So if somebody finds it for a given system, he will be a big deal. 100 years, nobody is able to do it. So always we use some sort of a ad hoc way or a heuristic way to find the Lyapunov function. Yeah. So that's a very powerful, and I think, I don't know where you know, this guy is a Russian mathematician. So 1955, Russia was ahead of space, you know that. Sputnik and all. US was behind. So it's basically Kennedy who did that. And you know what people didn't know was the state space. So there is a guy by name Parkes, 1955. He wrote a paper. He translated the Russian into English. That's a very classical paper. And Russians were far ahead. And he did that. That paper is classic. So my advisor had on his board. Everybody, control guys, have that. That's a very classic paper. So that paper was published in 1955. Then people realized what the heck is going on. How do you do that for multi-dimensional systems? Because in order to send a satellite, it's a multi-input, multi-output systems. So you need the state space representation, and Russians were far ahead. So this Park, that paper was a classic paper. He understood that a little bit on the Russian side, and then he converted that to English. And then all these people started working on it. Ackerman, all this came after that. Yeah. So then US guys were sent the thing, you know. Yeah. So they were far ahead at that time in terms of all this. So Lyapunov is a big guy, honestly. Unfortunately, he passed away. So we still struggle to come up with a Lyapunov function. If you know the Lyapunov function, then you probably have a solution. The challenge is coming up with a Lyapunov function that is positive definite, and the first derivative or the difference being negative definite. Okay. So in any case, in this example, so you see that L of x of k plus 1 minus this, that first difference has to be less than with alpha, and alpha is between 0 and 1, then it's negative definite. Then for any time instant, that L of x of k can be expressed in terms of bounded initial Lyapunov function L of x of 0 and a constant alpha. So this is basically bound, but if k goes to infinity, if I stretch it, then you see that L becomes 0, that means the bound will become 0, then it becomes asymptotically stable. Okay? So we were deriving all this with my students. So here is a Q function. All this is pretty same, except that you have a E. See, otherwise this whole derivation is same as what I showed you before. You see that? The bottom, you see there is that ZK and UK, that H matrix that we talked about. Now we call that as expected value of psi k, because this is a random, with random variables. And use the same Q learning, and you show some properties, it converges, and all this stuff I can skip, because now here is AZK and BZ. Okay. What is going on? Okay. So here is the model free tuning. So you see that model free tuning is there's no targets. So this is the value function. You write it using Kronecker product, but except that you have the expected value. That expected value over the delays and packet losses. Okay. This is the notation we use. This is the terminal constraint. So here is the unknown parameters. Here is the basis function using Kronecker, and basically you do that adaptive control. You convert this into an adaptive control problem, and then you come up with the update law. So there are two terms. You see, this is the Bellman error, and there's also final constraint error. So this mathematics sometimes will confuse you, but it's the same steps that I did, except these are stochastic. Bellman and terminal constraint error. Now, why do we need a terminal constraint error here? Why do we need it? So why do we need the terminal constraint error? I already explained it. That's why I asked you this question. I see everybody kind of staring. Now, why do we need two errors? Remember, there are two errors. One is the Bellman error, other is the terminal constraint error. Now, why do we need the terminal constraint error? It is a finite horizon. Finite horizon, you have a terminal constraint. If it becomes infinite horizon, that terminal constraint error will become 0. Don't forget that. So that's why it has both Bellman and terminal constraint error. The only thing is the formulation is in terms of E, which is the expected value. Otherwise, it's the same. And then you construct the historical Bellman residual, and you come up with the same update law that I gave you. So everything now is mean, AE error, boundedness, and so forth. Because remember, we studied in the morning, asymptotically stable becomes asymptotically stable in the mean. And that's what we are doing. Okay. And then you show the optimal control input, the same equation. You see that the inverse of that multiplied by the other term times the ZK. That becomes the UK hat. Here is the flow chart. The flow chart is same as the deterministic case, except that you have the E. Okay. So you have the terminal constraint error, you have the Bellman error, and then you come up with the update laws. You update it, you construct the U hat, and then you basically change the time. So the code is there. I gave you the code. You guys can play with it. Okay. These are all theoretical results. Here is a table that basically gives you the stochastic optimal regulator. Here is the controller. So you can see in there, this is the Q function estimator. It has two errors, Bellman as well as the terminal constraint error. So you see the Bellman equation error, the terminal constraint error that's going in. You're constructing the matrix H, and from there you're unpacking it, and then you take the bottom row, the diagonal element inverse of that multiplied by the first element, and that gives you the KK, the Kalman gain, which is L hat K. That's your optimal policy. You apply that to the system. So here you don't need A and B. So the same idea that you did with a deterministic system, you are extending that to the network control system, stochastic. And that's the only difference. Otherwise, it's just identical. The notations are different, but otherwise the same. Okay? So let's take a different example. So in this case, it's a batch reactor. It's a linearized version. Batch reactor is a nonlinear system, but this is a linearized version, just like F16. Okay? So you have the A matrix, you have a B. matrix. This is a matrix, not a vector. So you assume this is unknown. So I used the initial, so here is the augmented state, x of k, u of k minus 1, u of k minus 2. So this is a 3 by 1 augmented system, okay? So here is the initial admissible control, u naught. So remember that I said what is admissible control? Admissible control is to make sure that it makes the cost function what? Huh? Finite. The cost function finite, less than infinity. And so you need to start that. That's the right, we call that as a right initial step. So sometimes it's very difficult to find this. Okay, there are ways to do it, but it's very difficult. That's one of the problems with it. You can relax it. The former student Travis, he did that to relax it, but the Lyapunov proof becomes really cumbersome. You can relax it. But the problem is, if the system is unknown, always people ask this question, how do you determine the initial admissible control? Yeah. If I don't know AZK, BZK, how can I come up with the initial admissible control? Homework. So check that out. So how to define the initial admissible control when AZK and BZK, when the system dynamics are unknown? Okay. So I'm going to ask you tomorrow, like one at a time, and I'm going to call your name. So better you spend some time. So I'm going to call your name and say, hey, tell me what you found out. So make sure you spend some time after the class. We're going to end at 4 o'clock. And you spend some time trying to read the material. I think he's going to send you the slides. Read the material. Search the Google. Got it? Okay. So the question is, if I don't know the system dynamics, how do I determine initial admissible control? You understand that? Yeah. Okay. So here you see that the regulation errors converge, the control inputs go to 0, and look at that how quickly they converge. So basically it learns pretty quickly, very fast. Okay. And you see that there are two errors. One is the Bellman error. The other one is the terminal constraint error. It also goes to 0. So the total estimation error is basically the Bellman error as well as the terminal constraint error. And when n goes to infinity, that means that the final time is stretched to infinity. That means it becomes finite horizon. Is it finite? Infinite horizon, right? That's what that is. Okay, the errors always go to 0. So this is the total error goes to 0. Now look at that. I compared the cost. There are two plots here. One is proposed ADP, Adaptive Dynamic Programming Based Optimal Design for unknown NCS. The second was traditional optimal design with known NCS dynamics. So I want to compare the traditional method. So that means that I assumed that I know all the delays and packet losses. I want to see whether my approach, which is unknown, works close enough. So you can see that. So this is red is basically everything is known. And my blue is basically AZK and BZK is unknown. So there is an error, right? There is some error. That's why you see that error. But what happens as the time progresses, within about 1.5 seconds, you see how both of them converge and they become 0. It's very fast. Okay. So now you can actually look at the effect of Q matrix, Q and R. Q is basically used to weigh the X transpose QX, the state. R is basically used to weigh the control input. Remember I told you in the morning, if you crank up Q, that means you really want the X to converge very fast. In a tracking problem, it's like E minus X desired. When you crank up Q, that means you want that X minus XT quickly to go to 0. If you crank up R, basically you want the U to be small as possible. Okay? So you can see here. So I hope we have plotted different values of Q, 0.1, 1 and 5. So as you crank up Q from 0.1 to Y, see the 0.1 is green red is 1, and look at the blue, it's 5. So what happens? The norm of the states will become quicker, go to 0, much faster. As the same way, if you crank up R from 0.1 to 5, you see the blue is basically 5. So those are weighting matrices. So as you crank up, you drive the system faster. Now tell me guys, what happens when you crank up? What is the drawback? What is the drawback? Everything has a, there is a saying, no free lunch. Have you heard that before? No free lunch. That's what we call. So, like, when you see sales, here also in the malls they put sales, right? Really is the sale? That guy is putting as a sale? No. Basically, sale means he's not going to go bankrupt, right? He basically still makes money, but it's not as much money as when he basically no sale. But remember, a lot of people try to go and buy it. When they think, oh, it's 20% off. Is that what you guys do here also? Because in US, people are mad about it. But what they don't realize is that guy is smarter than them. He's not going bankrupt, right? He puts on sale, so people come and buy it. But actually that means that, look at this cost. It's much higher. He's basically jacking up the price. Yeah. That's what he's doing. Okay? So what is the drawback? What I'm saying is, oh yeah, you can raise those Qs and Rs as much you want, but where do we pay the price? Remember, engineering is a bunch of, you have to satisfy so many things. You can't just increase. That's why I said no free lunch. When somebody is taking you for lunch free, there is a reason why. Okay? So that's what it means. Nobody is going to give you free lunch. So the same thing with any of the design, there is always trade-offs. You cannot arbitrarily raise some of the values without paying something penalty. So this is your homework now. So what is the trade-off? Why can't we change the value, So that's important because there are reasons, and you guys can play it with in your code. Yeah, try it out. Okay? And this is important because you will do this. If you're in industry working, we have to do it. And now remember, these students, deliberately they're adjusting those values so you get a very nice result. Right? That's always happens, right? Because they never will go to a professor and show them a bad result. I never saw a student coming to me and say, it didn't work. So I think it's always important to, to vary those values and try it out. Okay? So this is important. There's a lot of trade-offs. Okay, so extend into infinite horizon. I think this is tomorrow's lecture. We may take a break? Yeah, that's fine. Excellent. So we'll take a 5-minute break because I think we'll try to cover this also. Huh? Oh, that's nice of you. The procedure is identical, like you do in the finite horizon. Okay? So here is the Bellman equation. You remember that E stands for the expected value. And then you use the least squares. You first construct the history, because that's the data from the reinforcement learning. And then basically once you get it, you are trying to minimize the error square, E square, Bellman error. And you take the gradient and you want to drive it to 0. And that's what the update law is. Okay? So you get the update law, and see, you end up in getting like this. So this is basically exponentially stable. The error goes to 0 by using that this update law. That's what it's basically showing you. Okay? So then Bellman equation in terms of the estimation errors. So you do that in terms of the theta tilde. Theta is basically the G matrix. You're converting into a vector by using the Kronecker product, right? And then you basically write in terms of the Bellman error, and then you pose it as an adaptive control problem. You come up with that update law, and the goal of the update law is to drive that G tilde to 0. Remember that. That's what we are doing here. And so what you can say is convergence of the stochastic cost function with adaptive estimation error is demonstrated given an initial admissible control policy. So you still need the control policy initial value to be admissible. Remember that. If you have only stabilizing, it's not enough, because the cost function has to be finite. The linear NCS time varying dynamics are shown to be asymptotically stable in the mean. So basically the errors go to 0 and it's asymptotically stable in the mean, because the mean error goes to 0, not the instantaneous error. That's the difference between stochastic and a deterministic. Okay? Overall stability needs to be proven. You have to show that and use the Lyapunov. So here we show that, and we show the convergence of that, and you can see as k tends to infinity, the E of z of k goes to 0, E of theta tilde of k also goes to 0, V hat converges to V, and E of U hat, expected value of U hat, the optimal estimated optimal control policy converges to the true optimal control policy. So that's what the theorem basically saying. The proofs are in the book or in the papers. Take a look at it. Here it says refer to appendix 3D. Probably there's an appendix in the book that should have the proofs. Those are Lyapunov proofs. Okay, so here is the update law, or the table, which essentially shows here is the optimal control policy in terms of H. Then you compute the Bellman error, and you compute the parameter estimate, and then you go back as k becomes k plus 1 and so forth. So asymptotically stable in the mean. I just give you revisiting the definition. An equilibrium point is said to be asymptotically stable in the mean if there exists a positive constant r for every initial condition. You pick x of t naught less than r, such that E of x of t minus x of e goes to 0 as t tends to infinity, where the norm denotes the Frobenius norm, and this expectation is a mathematical expectation. So that's how you define asymptotically stable in the mean or asymptotically stable in the mean square. People use either the mean or mean square in the stochastic domain. Okay? And then you can also do ultimately bounded, uniformly bounded in the mean or in the mean square. You can do both. Mean square means that norm, the expected value of x of t minus xe, you have a square there. Then you show that that term basically is asymptotically stable in the mean square. Okay? And it comes out like that when you do the Lyapunov proof. So check the proof. Okay? So I think, let's see here, what is this? So this is the same thing that for infinite horizon, you build the H matrix. Okay, you don't have terminal constraint error. Then you have the update law. You see that temporal difference error, j hat minus j hat of k minus 1 plus r, that's the temporal difference error. So these slides I added so that you don't have to flip your notes. You can actually use the same thing, you know. And this is a deterministic case, and here is the way you relate this to the actual optimal control input, and then overall stability for infinite horizon. You take the batch reactor example 3.2, you should have a code 3_2 in that MATLAB code. So it's a batch reactor. You can see in the batch reactor I have the A matrix. Here is the B matrix. This is continuous time. Now we have incorporated the network effects. You see the delays? This is the random delay. You see that this is for the other one. So we assume the sampling interval is 0.1 second. The bound on the delay is 2, d bar equal to 2. The random delay's expected value of sensor to controller is 0.08 seconds. Expected value of the controller to the actuator is 0.15 seconds. The packet losses follow Bernoulli distribution. These are all coming from stochastic control theory, you know. So you see that that's the packet loss. When it goes down to 0, that means packet is lost. So this is a Bernoulli distribution. Okay, so packet is not lost and lost. Lost means it goes to 0. So basically you create in the simulation, and you can guys could check it. So we create that, and here is the initial admissible control. Okay, and this is in this is somebody else's work. So this was one of the works of my advisor. This is my work. I'm kind of comparing it. Regression function and parameters. Remember, this is the Kronecker function as part of that H matrix. Okay. So now look at that. If I don't consider the network imperfections, the optimal control blows up. And why does it blow up? Because the traditional optimal controller cannot handle when you have delays and packet losses. You understand that? So that blows up, right? So since the network imperfections are considered, let's say if I consider them, assuming that everything is fine, nicely, you see that how nicely it converges. Okay? And here is the value function. So you will see when you plot it, you start anywhere here, you're trying to minimize it, and ultimately you reach the bottom of the valley. So I don't think you have these plots in the code, but you can write by yourself some MATLAB, and then you basically show that you know where it starts, and you see the trajectory going all the way down, and it reaches the bottom of the valley. You see that? It's like it either sides, and then it comes, and then that's where the bottom is. That's the minimum value. Now remember, I don't know, have you told about the assessment at the end? Okay, so the understanding between him and I is, it's going to be very tough, and most of you, majority has to really work hard to get the assessment. So make sure that that's how we discussed. So you may want to spend good amount of time going through the slides, running the MATLAB code, play with the code. Remember that. That's why we spend a lot of time, essentially making sure that you play with it so you understand it. Got it? So there is an assessment. This is last. So like an exam. How many of you know there's an exam? All of you know? Okay. So I think these plots are not there, but I think you can plot it. So this is the estimated Q function. So basically you want to see, you can actually plot that Z1, Z2 and start the initial value, and you can plot the trajectory. And as the controller is working, you will see that it tries to minimize that and show that it reaches the bottom of the valley. It's showing that the minimum value, okay? And here is the regulation error, and you can see that there are two plots. One is the adaptive estimator error based optimal control, and the other one is AE based suboptimal control. Now what is the difference? Optimal control is basically the finite horizon. The suboptimal is the steady state solution. You take the steady state gain after it converged, and you use that as part of the control input. So because of the steady state, you're using the steady state gain, the cost is higher than the time varying gain that you are using. So the time varying gain basically gives you the lowest cost. But why do you use the suboptimal? Because suppose you cannot compute it in real time. Let's say you are unable to compute because the gains are changing with respect to time. Then what you can do is, lot of industries this do, they run this code offline and they find out the steady state value of the gains after they converge. They use those steady state value in the control input. So what happens is, it's a little bit higher than the optimal cost, but is better than if you are not using the optimal controller design. So let's say you're using pole placement. You understand what pole placement controller, right? So if you do a pole placement controller, like on that day we were talking about desired poles, and then you place that, you are not optimizing it. Always the suboptimal is better than the pole placement controller. And the benefit of a suboptimal is, the controller gains doesn't have to vary with respect to time. That's the benefit. Always the optimal controller gains vary with respect to time. Remember that. So if the gains are a matrix, that's the problem, because you need computing power. And when you are doing it in real time, that the matrix has to be updated, because the gains have to be updated every sampling instant. But let me say this to you. We implemented many, I used to think that you need a powerful computers, okay? Always I go back to my childhood, right? When I was an undergraduate student. Now I think people hardly knows this. So you know 8086 processors? Do you use 8086 now? No. So we have implemented observer, neural network, actor and critique. If you have time, I'll show you some demos, okay? On an 8086 processor. It works. This is a formation control of mobile robots. So 8086, the only difficulty we had, my students were implementing, is the memory requirements. Because the neural networks have matrices, right? Remember that. We were using single neural networks. So those matrices, basically we are swapping it, because we don't want to save all those matrix values, you know? So we have to swap, and when we were swapping it, we had trouble saving those matrix values, because we had an observer, we had an actor, we had a critique. So we were able to implement in 8086, I think it's a 8-bit or 16-bit processor. 16-bit? Yeah, 16-bit processor. So some of this what I'm teaching you, you can do that. I have many implementations hardware. And I do for Boeing, quite a bit of Boeing implementations, aerospace systems. So, yeah. So we have time, like he said, extra time, you know, but not today. We have the cricket match, but if we have extra time, I can show you some videos where these were hardware implementations and stuff. So that time we may have to turn off the video recording, you know. So I can show you some hardware, hopefully, okay? So you see the difference between the two plots. One is suboptimal, other is optimal. Suboptimal means you take the optimal controller, you run it for a long time, and once it converges, the gains converge. You can plot the gains, it converges. Once it converges, you take the steady state optimal gains and you use them instead of the time varying gains. That's what we call suboptimal. Okay? All right? Okay. So here is the difference, you know, AE based optimal and suboptimal. Control inputs, difference between the control inputs. There are a lot of plots here. Okay, so I will leave the skip that part, and I think that's all we did. So we kind of went fast. We were 10 minutes ahead of time. Thank God to India versus Australia match. So any questions, guys? We have 10 minutes. Any questions? So this is lectures 3 and 4. So maybe we are ahead. So we may spend some time maybe. So any questions, guys? Yeah, I think I do want to take some questions if you have some. But remember, please use the code. I think you're going to provide, you already did that? You shared the code, yeah. Yeah. So I think you know, what I would suggest is try it out, the MATLAB code, because you need to do the MATLAB code running for the RL, intro to RL, right? That is the deterministic case. One has the policy value iteration code, the other one is the time driven, okay? Because we're going to use the time driven, but I want you to run that too and look at it, you know? So then he will share today the code for this, because we have the tutorial, right, where you want to run it, and then, you know, and see if it converges, and I want you to play with it. Change this, like the professor was asking, how does the cues affect? I want you to play with those. Okay, and you can break it. That's the goal of the code, right? Because it's a MATLAB. Yeah. So try doing that, and we'll see. Okay. Any questions? Yeah. Right, because as part of the A and B, right? That is clear, right? That's very good. Okay, what else? Right. So one is, remember, let me say with my experience, okay, the more you know, the better will be the design, always. Okay, so that's the first thing, right? All this we are doing is because we are saying that something is unknown, not everything is unknown, right? So if you look at the assumption, even in the simulations I showed you just a few minutes ago, you really need to know the delay bound. Okay, so in other words, you can't really design a system completely useless. Right? Remember, I told you, that's why I asked you to Google about what is controllability and observability. And a lot of times I have faced, when I was in Caterpillar, people come back, the mechanical guys design something, they completely ignore the control. They'll say, okay, here is the control, you're a headache. And sometimes what happens is that system may be completely useless. Because for them, they try to have a separate set of performance. You see? So the one thing that we put that limit is, well, you can't have completely open loop, right? So the delay has to be some finite quantity, right? So it's random, we know that. So that's why we have the protocol. Remember, we don't cover this, but it's in the book, okay? So that protocol essentially dictates what is the level of delay. So in the internet, sometimes the packet gets lost and you never get back the feedback. So that delay is infinity, but you can't really design something in real time with the infinite delay. So we always have to have some finite quantity. Yeah. So the thing is, all this stuff we are assuming, even though it's varying, that's why we assume that it forms a distribution. And that distribution has a finite property. You see? It has a finite property. So that finite property gives you the bound. Otherwise, you can't design. Yeah. You see? So that's important. So you have a bound. That's why I said the D bar has a bound. 2, 4, Yeah. Okay, yeah. That is correct. That is correct. Varying system. Okay, we do. Okay, there's a difference. Remember, I think I might have mentioned there's a difference, because the linear parameter varying systems sometimes have certain properties, right? There are also literature on time delay systems. But there, in the time delay systems, usually the delays are considered as a constant value. And yeah, most of the work, they never deal with the varying, So this is the difference between the actual NCS and the same thing with the linear parameter varying. Because you can use some of the adaptive control concepts, we did use them, like persistency of excitation. So we do bring some of those from the linear parameter varying. So yeah, it's a very similar, because there also the things are varying, right? So the only difference we have done, yeah, that's right. And we extended that to the stochastic domain, and by modeling it properly, like how do we get that into because it was not known before then. How to, remember I showed you even how the traditional stochastic control people looked at it. They always had A and B deterministic, and only the process and the noise is there. That's how the Kalman filter is derived. You see? Yeah. So that's the difference. No, there are other formulations people have done, like without doing this. But what I mean is, there are some issues, because when you do that, there are some approximations and all that. This basically gives you to bring in the protocol effect. So you are bringing in that network as part of it, and you can study attacks, security problems. And the computer science people are not knowledgeable, right? Because we know about the system behavior, overshoot, undershoot. So when you attack one of those things, it really causes problems, right? But the CS people don't understand that. So there are a lot of things this type of modeling opens up. The security is a big deal. And you know probably how Americans got access to Iranian centrifuges. Do you know that story? Oh, you don't know that? Oh, you're missing something. Okay, so you know that they want to know how Iran was developing the nuclear thing. So what they did was, they had the PLCs. So PLCs are not as good as other embedded processors. So they bought PLCs from Allen Bradley or one of those companies, the American companies. So they nicely wrote a software program that goes around and accesses all those things. So they were monitoring in secret the nuclear things, what they were doing, and they were slowing it down without Iranians knowing it. It's a big deal. It's published. Yeah. So they were creating some attacks to slow down the centrifuges of the nuclear, so that it doesn't become a kind of a grade, plutonium or whatever they were using, that you can build a nuclear, whatever. Yeah. So these PLCs, the PLCs are much more problematic because it doesn't have a lot of security. That's why. So when you deal with all these systems, network control and all, on one side is good, on the other side, I had some slides in the intro, I skipped them. Maybe we'll cover them in the part of the future. You can actually create some signals and you can attack a sensor or actuator. So I don't know whether you know, probably it might be of use to you. So there is a guy who is very smart, and there were real things here. So one of the guys were like, a lady was driving, he's shown on the real TV. He said, I'm going to control that car that lady is driving. This is an American car, and he had it with his laptop, and he controlled it. That lady who was driving on the highway, she lost control. She doesn't know. She was trying to turn the wheels, but the car is not doing, so I have a video. So people can actually control the vehicles if that particular, how he got involved? Through the CAN bus. So there are some danger things when you have a network inside the feedback loop, and if that network is a wireless network, it's even more dangerous. Somebody can eavesdrop and they can vary those parameters. That's what has happened. In that case, the lady lost. Lost means basically she didn't crash or anything, but she couldn't control the vehicle, and it's already being controlled by the guy remotely. She was trying to brake it and it's not braking. Yeah. So a lot of things. There was a Boeing aircraft. He was using that monitor. Remember, on a plane, if you travel long distance, you have a little thing on the screen, and somebody went through the screen and controlled the plane's speed and other things. They arrested him. Oh yeah, very smart people, but in a bad way. So there is a danger when you have a network inside that loop. The danger is basically there's a security threat, and that's a problem. So you got to be careful, because let's assume that you have to drive a process control. You are using a network-based process control. Imagine if somebody really want to cause a damage, they can really change some things, right? And so let's say if Tide or some other soap are being made, you can change some parameters, and that basically comes out garbage. Yeah. So there is that, it's good in one way, network control systems, but there are also some bad stuff can happen. So I skipped that few slides. Maybe when we have a closing session, I will go back. Okay, and we have time, I can play some videos. So we also did some attacks, we call that as a resilient control. So when there are attacks, how do you basically, so somebody can vary the sensor values on the fly, or somebody can change the control values. Yeah. Think about it. Right. 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 So initial admissible means the initial value is to be in the right selection. It has to be admissible for that system. And if you don't start with that value, the subsequent values that the network or the controller is going to generate will not be admissible. Okay, so right. No, it's not the equation. It's basically the admissible. Has to be admissible. There's no equation there. That is correct. And the reason you need that is because as you are computing the further future control values, it has to make sure that future values are also admissible. That's right. But if you don't choose the initial value, there is no guarantee that the future values will be admissible. So that these controller designs assume that the U0, which is the initial value, is deterministic but admissible. So mathematically, then only you can prove that the further values you are computing, U1, U2, they will be continue to remain as admissible. Yeah, that is correct. That is correct. That is correct. Okay, any other questions? It's 4 o'clock. Yeah. Right. It will go to what? Right, X. So it actually forces the X to converge to 0. That is correct. That is right. 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 Yeah, you can adjust that in real time, but typically we don't want to do that. So what you do is typically, in most cases, you play with those before you deploy them. And you want to look at it, what are the trade-offs? So what will happen when you really try to increase the Q value or increase the R value? So what I mean is, you really want to find out what is your limits. But I don't think you want to vary it in the kind of a missile scenario. You don't want to do that. Because in order to do that, you have to have a wireless or some sort of a communication, right? And imagine if you can do it, somebody else can also do it. Right, right. No, but what I mean is, I don't know whether you want to vary them because you want to fix them, but you want to first see in the simulation how those values affect. Yeah. I think it's this noise. Oh, speakers, it's basic interference. Yeah. All right, any other final questions, guys? All right, so I think I'm going to stop here. We'll close it. Tomorrow we have a lecture in the morning, 10 to 12. In the afternoon, there's a tutorial, right? So the tutorial will have the background on Lyapunov stability and also running the MATLAB code. So we just be around and you guys run it, play with it. It does work, we have proven that. So you run it and see what are the extremes. But what I suggest is before you run the MATLAB code, go through the slides. Dr. Bera is going to provide you. I would encourage you to just spend a little time. I try to, don't worry about the detailed math because I think we didn't go through those details, right? but I suggest you to see how the Q-learning is done and how we basically were trying to overcome the A and B. Remember that? And how the optimal stuff is, we are claiming is optimal. Those kind of things you want to try to understand that. And what are the variables that you can adjust so that when you run the code, you can try to vary multiple times, make sure that you don't keep overwriting it, then it's very difficult. But what I do is you comment out and vary some values and see what happens. Now remember, I told you before, you won't get exactly what I showed you on the slides. Why? Huh? No. Because there's randomness. Remember that? So there is a thing what they do with the stochastic variables they call Monte Carlo simulations. Have you heard of Monte Carlo? What does it mean? What do you do in Monte Carlo? We repeat the experiment with different initial conditions, and then we do what? Right. You basically average them out. So that's what you do. So some of those results have been ran 10,000 times because that's how we present them. So that's why I said when you're running them, you may not get exactly the same plots, but it will be very generic because you're also initializing the initial value sometimes. That also has some randomness. So this is basically how it is different from a deterministic system. In a deterministic system, you run it always, you get the same result. Okay? All right, guys, I'll see you tomorrow at 10 o'clock.